Yeah, unfortunately, it sounds like the city of Longmont has access to my Google Calendar because they always start wood chipping. Sorry. Yeah, so welcome to our second fully virtual AMWG working group meeting, joint with Whole Chemistry and Chemistry Climate. Here are some emails in case you have issues with the meeting or any of the logistics. You can see the agenda at the link on the screen. Here is our code of conduct. I think most of it is fairly self-evident. So yeah, please just be constructive and so forth. Here are the logistics for asking a question. Everyone's muted by default. We ask you to raise your hand using the raise hand feature in Zoom, and just be aware that there will be a discussion period at the end of each session. So if we don't get to your question due to scheduling, etc., we will have a chance to get to it later. And for presenters, please try to send your presentations to Elizabeth Faircloth at fair@ucar.edu, so that in case there are technical difficulties, there's a fallback. Okay, so I'm going to go ahead and get going with the AMWG update. I'm speaking, but I've gotten lots of input from my co-chairs in AMWG, as well as other members of AMWG and the co-chairs from the other working groups. Here is the overall outline of what I'm going to be covering today. As you'll notice, as you may have noticed already, and you may have heard, we have had a rotation in the co-chairs. I'll be talking about developments for a bit, and at the end, I'll close with sort of a plea from our software group here at NCAR that AMWG CAM let some things go in order to make maintenance and development a little easier from the software engineering side. Okay, so first we have had a rotation of co-chairs. Peter Caldwell has stepped down after 6 years of service, and it was great to work with him. We're of course sad to see him go, but we're also very excited to welcome Kevin Reed of SUNY as a new external co-chair. Kevin's been very, deeply involved, as well as many of his students, with CAM and the AMWG for over 12 years. His current interests include climate extremes and the societal impacts. He's also done lots of work on idealized configurations for climate models, including CAM and CSM. And as I said, I think CSM and Christian and I are very excited at the prospect of working with him in the next couple of years on CAM and CSM. So thanks to Peter, and welcome to Kevin. Yeah, I think it's going to be very exciting to work with you. So thank you. Thanks for accepting our invitation. So here is another view of our agenda, just focusing on CAM development. I think over the last couple of years, it's become, if it wasn't obvious already, it has become kind of evident that we have really two basic missions. One is, I think, to develop a cutting edge climate model, and the other is to support community users who want to use CAM for their own research. This is a list of all the developments that I'll be talking about briefly. And I should say that in this talk, I'm going to be presenting very few actual results. I'm mostly hoping to give you an idea of where we're going with CAM, or where we'd like to go with CAM, and pointing you to other talks that will present results later in the meeting. So anyway, what this slide is trying to highlight is it's trying to divide our development into this sort of cutting edge climate model stream and our facilitating community research stream. The orange font indicates developments that I believe are really sort of aimed, maybe not uniquely aimed at facilitating use of CAM, but certainly certainly will contribute to CAM's usability by members of the community. So, for example, we're developing a cheaper version of our unified high-resolution, high-top model, which I'll talk about more. Die-core evaluation, I think, is an opportunity for community participation. And we have these other developments here, variable resolution, other parts of infrastructure, and simpler models, which really are, I think, aimed at making CAM a useful research tool for many members of the community. So I'm going to go ahead and start talking a little bit about CAM7 for climate. So this is meant to be understood as our effort to develop the next cutting edge version of CSM as a climate model. I'll talk a little bit more about our die-core development. For the moment, we're proceeding with spectral element. The other die-cores that have been under consideration, MPAS and FE3, will be functionally supported, and we may consider them depending on how things go with SE. But in the immediate term, we are sort of proceeding with the spectral element die-core as the dynamical core for the climate, and I keep emphasizing for the climate Cmaps class version of CSM. We have a new ocean model that requires enthalpy fluxes. This is proceeding with a short-term fixer, which Peter may discuss a little bit later in his talk. So the goal here is to produce a single Cmap class model with a top at around 80 kilometers to have a better resolved stratosphere. We want full chemistry, certainly as an option. And we are, as I mentioned earlier, also interested in providing a somewhat cheaper version with a lower top using simplified or no chemistry, and that's still under discussion for us. And both versions of this model will have increased Pbl resolution, and actually the vertical structure of both of these, both the full high top model and the slightly cheaper version, will share a vertical grid up to somewhere in the lower stratosphere. So this is a slide showing our new Pbl resolution in red compared with the old Pbl resolution. So you see there's there's been quite an increase in vertical resolution throughout the lower troposphere. We've roughly gone, you don't see it on this plot, but in the free troposphere above where you might expect the boundary layer to live, the resolution in the old vertical grid quickly approached 1,200 meters, and we're now down to about 500 meters. So on the right of the slide, you see one of our goals, which is to simulate at some level of, with some level of fidelity, simulate the equatorial, the tropical quasi-biennial wind oscillation in zonal wind. And this is what that shows, this plot. And you see the new model with DZ equal 500 is doing a decent job of reproducing the QBO. One thing that I'd like to, one thing that I believe is true also is that our increased vertical resolution in the boundary layer and free troposphere will give us better representation of many many physical processes in the troposphere that are important for climate. Adam Harrington provided this plot of cross-sectional plot of cloud fraction through these two important stratus to stratocumulus regions off the coast of California and also off the coast of Peru. And you can see that, the top panel in each case here is the old L32 version of the model with coarse resolution in the boundary layer and a resolution of around 1,200 meters in the free troposphere. And below, in each case, is the new 58 level model. And you can see that the general appearance of these cloud decks is just more geophysical in the higher resolution vertical in the higher resolution vertical grid. So remaining issues that we have in developing this unified model is a water vapor dry bias in the upper troposphere, lower stratosphere in the tropics. We believe this is related to reduced numerical diffusion, and we think it can be attacked by adding some physical diffusion in the tropics. There are other remaining biases that we will be getting to addressing in the next year or so. Stratospheric wind biases, we're going to be having a look at the climatologies of sudden stratospheric warmings, because as I mentioned earlier, one of the goals of having this unified model is to realistically represent stratospheric variability. And of course, we still have we have basic climate tuning to do, and this is especially the case now that we have incorporated an updated version of microphysics. It's scientifically Morris and Gettleman. The new acronym is PUMAS, but that has just been adopted into the model framework. And we're just beginning to evaluate the coupled system with this higher vertical resolution. So now I'm going to talk a little bit about physics developments. We have three climate process teams within NCAR that are addressing various aspects of boundary layer physics. You'll be hearing talks about all of these CPTs later today. They address, in shorthand, they're addressing momentum transport by club, introducing a new sort of coupling club with a mass flux shallow and actually shallow to deep mass flux parameterization. And there's the CLASP CPT, which is looking at coupling land surface heterogeneity into the atmosphere. PUMAS, as I mentioned earlier, is an updated version of microphysics. And this has now been incorporated into the CAM development branch, and you'll hear a talk from Andrew Gettleman on this later this afternoon. So this is a summary of kind of the key points in CAM 7 physics with a little bit of, just a bulletized status for each. Increased Pbl resolution, we're sort of there. We know what we want, and we're just tuning it. I haven't talked about physics reordering, but that is also in CAM development. reordered the calls to physics subroutines in a way that we think makes more sense. PUMAs, the new microphysics, has just been incorporated. We're now tuning it. The CPTs are, still they're in progress. I estimate there's a 1 to 2 year time frame incorporating results from these CPTs into the model. And Peter Lauritsen will talk later in the week about our attempts to sort of rationalize the energy in the model by introducing variable latent heats for different species, and sort of with the goal of having not only that, the goal is to have a more realistic representation of the atmosphere, but this will also allow us to put in consistent enthalpy fluxes that can be given to the ocean. And as I said, Peter will be talking about this later. So about the dicores. We have decided, based on input from dynamical core developers of MTAS and FP3, and in light of how much significant resources are required for a real formal dicrenter comparison, the SSC has recommended that we not do a formal intercomparison now. So that's the reason that we are sort of proceeding with the development of CAM7 using the spectral element dicore for the moment. But as I said, this is for climate, and the other two dicores, AMPCAS and FE3, will be functionally supported, and they are being incorporated into the CSM infrastructure. And I think this actually provides a nice opportunity for the community to apply for funding to help us compare these dicores in a full climate setup. I want to note that dicores will be discussed during a session on Wednesday morning, so you can hear more about this then. And finally, on this topic, I just want to point out this slide that I happened to get from someone from Peter Neely's presentation at the AMS. He has raised a few points about community modeling, and I think it's interesting that he has asked this question: is a community supermodel with multiple dynamic cores possible? And I believe that CSM really is that model now. So just wanted to show that to the community here. Okay, now on to regional refinement. Again, you'll be hearing more about this topic later in the week. There are comp sets that have been available for regionally refined grids, and these include the CONUS grid, continental US, and Arctic Greenland ice sheet grids. Sort of more on the development side is a high mountain Asia grid, which will be discussed by René Weingard on Wednesday afternoon, and Patrick Callahan will be talking about South America refined grid on Wednesday afternoon. Also, for those of you interested in variable mesh generation, Patrick Callahan will be giving a tutorial again on Thursday, 10 to 11:30. And please see the registration link in the message from Elizabeth. There was one this morning. I think it may be in the messages on subsequent mornings as well. Okay. Whoops. So now I'm just going to be talking a little bit about simpler models here. There is ongoing work on coupled simple model configurations, including a tool chain for generating bathymetry and continental geometry. There's progress on unifying SCAM with chemistry, improved comparisons with LES, etc. Gray radiation is complete, and we're just waiting for it to be incorporated into a CSM release. Our new co-chair, Kevin, has just published a paper on the radiative convective equilibrium configuration that's listed here. Other efforts that involve CSM that will be discussed, well, two of them will be discussed here this week. CMA, Andrew Gettleman will be talking about CMA, which is a unified framework for modeling being developed at NCAR. Earthworks, Bill Randall will discuss Earthworks on Wednesday. And in shorthand, Earthworks is an effort to do cloud permitting coupled modeling using a simple, using a single MPass grid for all components. So tune in on Wednesday to hear more about that. I'm not going to discuss this here, but there was a large ensemble conducted with CSM2. That's been completed, and the data sets were released to the community in the summer. And if you're interested in that, I should have put the names, but I encourage you to contact Gokhan Danabasolo and Isla Simpson if you're interested in that data. Brian Dobbins in our software group has been working on making CSM easier to use in the cloud. NCAR will start offering regular, frequent CSM training sometime again, I think this summer, via the cloud. And Brian expects these trainings will maybe start off at once per month, but may become even more frequent. So I think that's an exciting development for people interested in using, people in the community interested in using CSM. Mariana and others in the software working group have been working on improving or streamlining our coupling infrastructure. We've gone to the development has taken us to something called Cmaps, Community Mediator for Earth Prediction Systems. It's a collaborative development between NCAR and NOAA. And for me, the important and exciting part of this is that this should simplify greatly the generation of coupled of variable resolution configurations. So to close, I just want to close with this plea from our software group. It's becoming very difficult to keep things alive on the development front of CAM and CSM. Every time new physics or anything comes in, changes have to be implemented in 5 die cores, which are listed here. We have, by Steve Goldhaber's best estimate, 49 configurations of CAM physics, and these all have to be tested. So the bottom line is, I think, and this is something that we've been asked to think about by Gokhan, the CSM chief scientist, what parts of our current, development branch can we let go? I want to point out that things that we quote unquote let go in the development branch don't disappear. They are kept as part of older CAM and CSM tags. So, for example, a die core wouldn't disappear if we stop testing it in the CAM development branch, because it will remain as part of the release in which it was included in the first place. So with that, I'm gonna close, and I don't know if there's time for questions, but I'll be happy to take some if there is.
Thanks, Julio. I don't see a question in the chat right now, and also we are kind of out of time. I suggest that we move on. We have a 15-minute discussion period after the 3 introductory talks. So please, when you think of a question, please put it into the chat, and we then address it after the 3 overview talks. Next presentation will be by Nick Davis and I think 2 people, I guess Nick Pedatella, and it's about the state of Wacom.
We'll switch off at some point in the middle of the presentation.
Good. Okay. If you could leave a minute or so for questions. If not, then we push it into the discussion.
Okay, we'll do our best. All right, good morning, everyone. Thanks for the introduction. We'll give a brief overview of the state of Wacom. So my name is Nick Davis. My co-co-chair is Nick Pedatella, and our external co-chair, Jessica New, and liaison Mike Mills. So I want to talk mostly about some of the polar vortex and sudden stratospheric warming relevant dynamics in Wacom. Julio alluded to sort of conquering existing polar vortex biases in CSM more generally. But what I can do is sort of shed a little more light on those and how we think they may be impacting some of our results. So I'm showing you on the left some composites of the wind at 10 hectopascals and 60 north, sort of a standard measure of the polar vortex strength. And this is the seasonal cycle of daily average winds from 25-year simulations with different versions of chemistry. So comprehensive chemistry in the upper left, middle atmosphere truncated chemistry in the middle, and then a middle atmosphere chemistry run on the 2-degree resolution grid. And these are all for the finite volume dynamical core. And so the shading shows you the actual distribution of winds from Wacom, and the red lines give you the minimum, maximum, and then median winds from Meritu. And what you can see is that from about November through January, the Wacom median winds tend to be weaker than in Meritu. You can also see that the maximum wind speeds are substantially weaker throughout the winter season. So essentially what we see is that the wind distribution in Wacom is more symmetric throughout much of the year. And then it sort of flips later in the year. We're slightly faster than observed. This might be related to more symmetric and generally stronger wave forcing in the model, but we're initiating a project now to understand exactly what's going on there. This bias could affect some aspects of the CSM2 S2S forecasts, which I will briefly mention in a second. But it's important to keep in mind these biases. They don't look big, but they're on the order of up to 30 to 40%, depending upon the time of year. And that can be a pretty big difference, especially when we're talking about sudden stratospheric warmings. So I wanted to show the distribution of sudden stratospheric warming frequency by month in these different flavors of Wacom, using 2 different definitions just to show that the results are relatively robust. So there's a standard definition for sudden stratospheric warmings where the 10 hectopascal 60 north zonal wind reverses with no subsequent reversal for 20 days. So the idea is that you want to not detect things like final warmings. But there's nothing necessarily special about 20 days. So you can come up with a lot of different objective definitions that are adaptive to the sort of dynamical scene. One is to just say that the integrated subsequent westerly winds are at least as large as the integrated easterly winds during the sudden warming. And I'm shown on the right here the frequency by each ensemble member that we've run for the historical simulations versus MERA. And a red X indicates when that ensemble member is statistically significantly different from MERA2. So it's really only in November that Wacom has a statistically significantly different sudden warming frequency than the observations. And that's primarily because there's no sudden warmings in the observational record in November. And again, that we think has to do with the weak vortex throughout the early part of the winter in Wacom. There's some sense that in spring, some of the MA simulations might show too few, but again, it's not a big difference. So how does this play out in terms of impacts on the science? Well, right now, this will probably get talked about, I think, in the Earth System Prediction Working Group meeting, but the full description and evaluation of the CSM2 Earth System Prediction, sort of S2S platform, has been revised right now for weather and forecasting. There are real-time forecasts being kicked off every week. On the left, this is showing you some of the real-time diagnostics from the Wacom website, showing you the zonal mean zonal wind predictions right now. And you can see Wacom is actually predicting a high likelihood of a sudden warming in February. So we want to nail down these biases to make sure that, for example, this drift between Wacom and CAM isn't due to a mean bias in the model. There's also a lot of new science papers coming out of the S2S platform. I encourage you to keep on top of those and also potentially consider participating in using the output. It is available in the research archives. Finally, I want to talk about Wacom with regional refinement, the spectral element die core. So this was part of an NSC project over the last couple of years that got extended just due to some stability issues with the spectral element die core running with 110 level Wacom. But we've already completed one simulated year with the 8th degree CONUS refinement. We saved every time step output from this model simulation. So it was actually quite expensive. That takes a lot of computational time writing all that output just to run the model. So the purpose of this project was to try to understand some of the resolved gravity wave dynamics when we get down to 1/8 degree refinement. And on the right, I'm showing you a mixed space-time spectral analysis of the vertical eddy momentum flux at 0.01 hectopascals, which is about the mesopause. And the shading shows you the power in meters squared per second per day per delta phase speed as a function of wavelength. And so you can see when we do the spectral analysis at all longitudes, we see some vertical eddy momentum flux power. But when we restrict that to the CONUS region, we see quite a large increase in power at most phase speeds and wavelengths. We also see an extension, obviously, into shorter and shorter wavelengths as we are resolving more and more of the spectrum. And we're using some of these results now to try to do a sort of brute force attempt at a scale adaptive gravity wave scheme. And the last thing I want to talk about is some of the improvements to physics that some folks are going to be talking about. Michael Weimer is going to talk about some gravity wave impacts on chemistry on Tuesday. So you can imagine that gravity waves, by virtue of their impacts on temperature variance, cause changes in chemical reactions. But that's not really felt by the current chemistry scheme because that's all contained within the gravity wave scheme. Dan's going to talk about some changes to the solar and geomagnetic forcing. And again, we're sort of starting to muse about how we can make a scale-aware gravity wave scheme. And I think these kind of physics developments and the community engagement are pointing us to seriously consider some of these new platforms like CIMA and Musica so that model development can keep up with science and user needs. And Andrew's going to give a general discussion of CIMA on Wednesday. And I think Louise is probably going to give a much bigger overview of Musica in the coming overview slides.
I will discuss a bit more on the upper atmosphere developments. So first, some work from Dan related to new methods for prescribing the solar and geomagnetic forcing. They've put together a nice Python code that it makes it a lot easier to update these in closer to real time, which makes it easier for us to run more recent time periods in the model. And then also added some new schemes for including the electron precipitation within the model. Could you go to next slide, please? Next, skip that one. And a lot of the work in Wacom X, the high top model, has been focused on development with the SE die core. As Julio mentioned earlier, we see that as the likely future for the model. So we have focused a lot of our development there, which allows us to go to much higher resolution. And the main thing, I think this was discussed in the summer meeting, was modifications to the species dependencies in the higher altitudes, and then also incorporating some molecular viscosity and thermal conduction in horizontal, and then also a regridding scheme to go between the SE coordinates frame and the geomagnetic grid that we use for the electrodynamics. And when we incorporate this on the right, you can see the FV dicore. This is polar projection of temperature at 400 kilometers. And then the bottom right is with the SE dicore. And you can see there's a lot more structuring in the temperature field at high latitudes, because we don't need to apply as much filtering in the spectral element model compared to the FV dicore. And recently, one issue with the SE dicore, especially at higher resolution, is it had quite large memory footprint, so it had to run on a high number of nodes. And Francis Witt has recently been working on addressing that, so that it runs a bit more efficiently in terms of the memory. Other developments, Liu has been running at the high resolution NE 120, which is roughly quarter degree or so horizontal. And I will show a bit of this on the next slide. And he also has a more detailed presentation on Wednesday. And there's some ongoing work in terms of coupling with a magnetospheric model in order to better capture the effects of solar and geomagnetic activity. And then some ongoing work in terms of meteorological constraint in the SE dicore with both nudging, and then we see using data assimilation, implementing that in the SE dicore, even though it's already in the FV dicore, will take some additional work. And as we adopt the SE dicore primarily, then we'll be using that for the data assimilation. Next slide, please. These are just a few quick highlights from the high resolution Wacom X model that I said. Hanli will discuss this more in a couple of days, but they've run from January to August of a free running simulation at a constant solar activity to look at essentially the wave driving of the upper atmosphere. And in this scheme, there's no parameterized gravity waves. And on the left, you can see the zonal forcing of the smaller scale waves in the colors. And then the contour is the zonal mean, zonal wind structure. And there's two main things to emphasize here. First, we do see there is a lot of contribution in the upper thermosphere from resolved smaller scale gravity waves. They are not going to be considered in the normal parameterization scheme. So this will impact the thermospheric circulation. And the other thing with running at this higher resolution, we get a much better, more realistic structure of the zonal mean, zonal winds. For example, in the Northern Hemisphere, the winds in the lower thermosphere, say around 100 kilometers, maintain a eastward direction, as opposed to typically in the FV dicore, they would be westward, which is contrary to observations. So we get a much better agreement here when running at the higher resolutions and resolving the gravity waves. And the right is perturbations in the total electron content at periods less than 2 hours. And you can see there's a lot of structuring in the ionosphere electron density fields due to resolving all of these smaller scale features. And Hanli will go into more detail on these in a couple of days. Next slide, please. And then we've also done some work in nudging Wacom X with the SE dicore with using the physics side, which we have not done before. We had only used the nudging to say mirror in the FE dicore, so had to include some new framework for that. And running that with the NE30 resolution, about 1 degree. On the left is observations of the total electron content variation over the American sector at 10 local time during the stratosphere warming during 2009. And you can see there's large amount of variability, say around a 20 to 30. And when we nudge the model on the right, we capture much a similar variation. It's not identical, but we would not expect just from constraint through the nudging that we would capture everything. But it's similar to what we would get when we nudge with FV die-core using dynamical nudging. So this suggests that we can effectively implement this nudging procedure into Wacom X with the SE die-core, and we're currently testing nudging at a higher resolution, so we can look at reproducing the smaller scale variability during specific time periods. Next slide. You can skip this slide as well. I think those were not to be included. Just briefly, we'll conclude here with a timeline of development that we had put together for the next few years. The main kind of near-term priorities, as we discussed, are focused on the Wacom X SE die-core and a regionally refined ComSet for Wacom that Nick Davis discussed earlier. And then we would like to include ComSets that can be used for initialized prediction. So it's easier for community members to perform those on their own. And then we have some other longer term development for improving community support. One is better TEM and transport diagnostics, especially for irregular grids, as Nick mentioned, saving for the regionally refined ComSet. Everywhere is partly necessary to do these diagnostics afterwards, and having that all in line would significantly improve things in terms of performance. And then also we would like to update the specified dynamics approach, so it's more consistent across both chemistry, dynamics, and physics. And then there's a number of updates to chemistry and physics throughout the model, both in the stratosphere and then as well in the thermosphere as well. And then we would also need to keep in mind integration with the higher top model that Julio mentioned, and then as well as developing a whole geospace model that would be fully coupled with a magnetosphere in terms of two-way coupling, and that work is ongoing. So we will conclude there and can take any questions.
Thanks, Nick and Nick. Are there any questions? Feel free to put them into the chat box. You can also raise your hand. I actually had wondered, you talked about the diffusion of filtering mechanisms. Are these die-cores using lots of Rayleigh friction at the very top of these models?
One of the issues with the FV die-core is, especially in the polar region, we have to add a filtering for the transport of O+, particularly. And that is really where a lot of this sort of diffusion comes from in the thermosphere. Mm-hmm. And it's not as necessary in the SE die-core.
Okay. But do you have a Rayleigh friction sponge?
Not a Rayleigh friction sponge, but there is a sponge at the top. Okay. Yes. And Peter, I think, just responded here. There's enhanced hyperviscosity and a Laplacian right at the top. Yeah.
Don't see more questions. So in this case, maybe we move on, and Louisa Ammons will provide us with an overview of the chemistry interactions and chemistry activities. And then again, we have a 15-minute discussion period.
Okay, thanks, Christian. Welcome, everybody. Good morning. I'll give a little overview of what we're doing in the chemistry climate working group. Sorry, bar in the way. So this is just sort of generally what the chemistry climate working group goals and our scientific motivations. But I wanted to mention that in the near term, our some of our broader goals are supporting the development of CAM7 with chemistry, and also developing a new aerosol interface that will really simplify changing aerosol schemes. So I just wanted to mention some of the things that we've been working on. We've talked about these at a number of working group meetings over the past couple of years, and you can keep track of their status. These are items that are now in issues in GitHub, and hopefully we'll be moving to the development branch soon. They include the HEMCO emissions handling module, and I'll talk a bit more about that in a minute. MAM5, which is adding a fifth mode to the modal aerosol model for stratospheric sulfate. New dust emissions, and Danny Lung will be talking about that tomorrow. Updated dry deposition of aerosols, the mosaic scheme that allows for nitrate and ammonium aerosols to be simulated, an update to DMS oxidation chemistry, but this depends on mosaic, and also the coupling of the GeoChem module into CESM. So these are all things in active progress of being put into the code. We have a number of other things that we're still working on. They're still in sort of scientific development, adding an online photolysis scheme, adding additional chemistry schemes, a simpler scheme for more climate-based studies, as well as more detailed chemistry, the short-lived halogens, which Nick just mentioned is of interest to Wacom as well. And Rafa and Carlos will talk about that on tomorrow morning. It's also work by Texas A&M on marine organic aerosols, a large group working on karma, the sectional model, groups at the University of Sheffield and Boston University are updating the online soil NOx emissions so that can be calculated real time in CESM. We're updating Megan, the UC Irvine group is working on that. And a big project that we hope to make good progress on in the next year or in the next few months is running CAM with MPAS with full tropospheric and stratospheric chemistry. And so if there's anything else that people are working on, we'd really like to hear about that and get in touch. So HEMCO is a tool that's been developed by Harvard and a lot of other groups to handle emissions and reading them in and combining different inventories, replacing global inventories with regional inventories where they're available, doing scaling like applying diurnal variation and vertical distribution, and provides conservative regridding to the model resolution. So you can specify a raw emissions data set and then have it regridded to the model resolution, which will be a really great benefit, especially for people who are making their own variable resolution grids. We also have, in the meantime, there are several offline tools, scripts available for regridding emission inventories to use in CESM on our GitHub and wiki pages. So as we mentioned, I'll say a bit more about Musica. So this is really our project with the goal of making more modular components for chemistry, various aspects of the chemistry and aerosols, as well as making them suitable for variable resolution and being valid across a wide range of resolutions in a single model. And this is all being done in partnership with CMA, the System for Integrated Modeling of the Atmosphere, which Andrew Gettleman will talk about on Wednesday, and you can see more at their webpage. And you can get a lot more information about Musica and overview on our Musica webpage and in the BAMS article that we published a couple of years ago. So Musica has a steering committee led by Mary Barth and has these working groups to help guide the development of these different components, being led by NCAR scientists as well as scientists from across the community, outside the community, and we're really inviting everyone who's interested to become involved in the development and using Musica. And you can see how to sign up, get on email lists, etc., at our Musica webpage. And one of the key parts of Musica is having a model-independent chemistry module, which we call MECM. And this includes a database that has how you specify reactions and reaction rates, the compound properties, photolysis, plug them into a chemical solver, and then through a standard interface, connect them to an atmosphere model. So we're still sort of waiting for what the standard interface will really be for CAM, but this is all now available in a box model that we call Music Box that's available on GitHub. And if you're at all interested in playing with that, I encourage you to download it and use it for comparing mechanisms or doing other science studies with a box model. And so Musica version 0 is the label we've given to a configuration of CAM-CHEM or Wacom using a regional refinement with the spectral element. And it's essentially just a comp set within CESM 2.2. For example, the FC nudged or FC hissed comp set, and specifying the resolution for this CONUS grid, which has 1/8 of a degree in this refined region over the continental US and 1 degree for the rest of the globe. We have a lot of information on the Musica wiki for how to run it, this configuration, and you can also create your own grid, we've already mentioned. And if you haven't seen any of the past tutorials, definitely join Patrick's tutorial on Thursday. And even if you have, there have been updates, and so Patrick will be telling everyone about those on Thursday morning. So this grid is rather expensive. So we've been running, we've run some simulations of the CONUS grid and posted them on the Geoscience Data Exchange of NCAR, formerly called the DASH repository. And currently we have 2012 to 2013 results available. But if you want other years, or you don't find the output that you want, we're certainly happy to help run simulations and provide the output to you. And one other activity that's part of Musica is called Melodies. It's a modular framework to compare model results and observations, primarily of atmospheric chemistry. And we've coupled this with a project called MONET, the Model and Observation Evaluation Toolkit, that has been started by NOAA. And we've been working closely with Becky Schwantes and Barry Baker at NOAA CSL here in Boulder, and the Air Resources Lab in Maryland. And it's all written in Python using some standard packages. We have Jupyter notebooks with examples, and it's configured with a YAML configuration file, which is just a text file like a name list. And the overall picture here is to have, it has objects for handling the models output, and an object for handling the measurements. And MONET does the pairing of these model and observations, produces plots and statistics. And the Melodies MONET part is really this configuration file. So you set everything up ahead of time, defining your model and your observations and what sort of plots you want. And then it all just runs and produces plots like this. It's currently running with WRF-Chem and surface observations, so you can have maps of the model results and the observations, or bar charts, box and whisker plots of the summary statistics. So we're going to show the community how to use this initial configuration in March as part of the Musica tutorial series. So please join us if you're interested. So I'm just going to show the rest of the time a few results from Musica version 0. I've shown these, or Becky Schwantes has shown these in the past, but her paper is about to be hopefully accepted in James. And it's really the first publication of this Musica version 0 with comprehensive chemistry on the CONUS grid. And one of the big findings was that at the finer resolution, there's a much bigger difference in the different chemical mechanisms than at coarser resolution. We know the changing resolutions certainly gives you a different distribution due to different emissions, but having different resolution also affects our understanding of the value of the how the chemistry behaves. And since there are a couple more weeks that people can look at AGU results, if you registered, I just thought I'd list here that there were several talks at AGU showing Musica version 0 results. A couple talks, Wenfu and Nori's talks used the CONUS grid. Baruz showed results from the grid he made over northern India. And Rebecca showed results for a grid she made over Australia. And people are working on several other grids. Dusong Zhou has a grid with 7 kilometers over South Korea and coarser resolutions gradually across the rest of East Asia to look at Korean air quality and the comparison of different horizontal resolutions compared to the coarse AQ observations. Wenfu has just created a grid over Africa, which takes up an entire cube face of the cube sphere with a 1/4 degree resolution over the whole continent. And we have a grid to support the ACLIP campaign with a 1/4 degree grid over all of East Asia. So if you're creating a grid, we'd love to hear about it. And we're hoping to create a library of these grids that once people have found that the simulations are stable, then we can make them available to the rest of the community. And another set of work being done looking at resolution is done by Xiao Hong with colleagues at IAP in Beijing, and looking at the impact of model resolution on dust and aerosols over China. And they've done 4 simulations at different horizontal resolutions with a finite volume and see great differences. Sorry, mouse. Seen large differences with resolution in the dust emissions, and also done a variable resolution with a 1/4 degree, 1/8 of a degree, seeing big differences compared to 1 degree SE, due largely to the topography. These results were done with CESM-1, and they're going to plan to do them with CESM-2 and also the new dusty scheme when that's ready. So just to finish up, I want to say that I'll be stepping down as co-chair, and Simona Tilmes will be taking over as the co-chair on March 1st. And taking Simone's place as liaison is Rebecca Bocholtz, who's a project scientist in ACOM, and she's been part of the ChemChem group since she's joined ACOM in 2014, and has already done a lot of work supporting the community through the development of the wiki, and has been doing a lot of chemistry climate research and air quality. And probably many of you know her related to some of the wildfire work. So thank you, Simone, and welcome to Rebecca. And I'll still be around, of course, see you all, even as not giving these semi-annual presentations. And just I'm closing with a list of web pages. We have a couple events coming up, the Musica tutorial series. If you haven't seen it, you're still welcome to register and join future sessions and find the videos for the past sessions. And I'm planning an ozone dry deposition workshop with Olivia Clifton and Arlene Fiore. And we'll have a web page on the ACOM website soon, just not quite up yet. And so if you're interested in this, please let me know. And if you're doing any research and development on chem, chemistry, climate interactions, tropospheric, stratospheric chemistry, air quality, please let us know. And we'd like to really build the community and share our research. That's all. Any questions?
Thanks, Louisa. Other questions? Again, you can put them into the chat or raise your hand. So there's one in the chat from Daniel Marsh. Seems there is some question about how Wacom is going to be integrated into Musica version 0. What are the roadblocks to creating an end-to-end system?
Well, I think it's really settling on a standard interface, such as CCPP, and being able to handle a flexible number of chemical compounds that have to be passed between components, because one of the key things we want to promote and be able to do with Musica is to make it straightforward to change the number of chemical species you have in the model. And that needs to be allowed to pass to other components flexibly. I think there are others who know far more about what the technical roadblocks are to that than I do. So I'm not sure I can say much more.
I had a question, and this is probably pretty generic, also addressing AMWG. You mentioned all these new variable resolution meshes, and we also learned from Julio that Cmaps will ease that interface or will ease the transition to variable resolution. Can you talk about the current status of the transition to Cmaps, and is this already in place? Can we easily now go to refined meshes?
I think not quite yet. How we have all been producing these grids is with offline tools. And there are a lot of tools that are released with CESM that it's a number of steps, but it's not difficult to produce all the input files that you need to create on the regrid things to be on your new grid. So, may take a day or two to get all the files ready, but it's quite doable. But so certainly having Cmaps, that will all be done online, and you won't have to prepare the additional files beforehand.
And this is also a question for Julio. What's the timeline for this transition to Cmaps?
Well, I think we already have runs that use nuOpsy as a coupler, and I think we validated that they are climate-wise the same as the MCT coupler. So those the nuOpsy coupling is already in the system.
But the functionality, and then I ask, I entertain other questions.
I can't speak to the ease, I can't speak to how this has been incorporated into the grid generation, but I see that Adam has his hand up. Maybe he has a better idea.
Well, I would just say in terms of timeline, I'm curious about what the timeline is to switch over CAM's regression tests to have a majority of nuOpsy regression tests. I think that's going to be the big step to make this more robust for the entire community. Working on it as we speak.
Yeah, so there are a few, yes, chat, if you monitor the chat, there are a few more comments here. So we are experimenting with Cmaps right now, and Steve Goldhaber says, if you run create new case today, Cmaps is the default driver, and we are working on it as we speak. So the transition, the ease for the variable resolution grid is coming, but it says, again, I'm just asking for the community here, are we talking about a few months or are we talking about a few more years?
Do you mean specifically for the variable
for
resolution?
the variable resolution measures?
I see.
Maybe Steve can actually comment on that.
I would guess months, but
okay.
That would be my guess.
Michael.
So variable resolution is available today. It's sort of an orthogonal topic from the driver.
Yes, okay.
But a lot of tools are still being developed and coming online to ease the transition to developing, I want to do an experiment with a new variable resolution grid. We're trying to make that workflow much more efficient. And that's coming up, hopefully over the next month or so.
Okay.
We'll have in place a better tool chain for idea to experiment.
Okay, and Patrick might talk about that also on Thursday.
He's part of that effort, yes.
Good, okay. So we have a question from Michael Prather. Luisa, thanks for the nice talk. My question is about how you plan to have a swappable radiation code for photolysis and cloud fields. You're getting to scales where radiation interacts with the neighboring columns.
Yes, that will be a challenge. That's not something I have directly thought about or working on, and so I'm not sure I can give much of an answer. And I don't know if anyone else online wants to help me out.
So Daniel Marsh.
I would argue that this issue has certainly come up for WRF, and I don't know whether it sounds like the issue is talking about sideways radiation.
Yeah, I think so.
As I said, I imagine the issue has come up in WRF, and we probably need to ask there at what resolution does it become really significant?
So Daniel Marsh comments, we are looking into using Socrates to address this. I'm not familiar with that. So
but he means unifying photolysis and the radiative transfer.
Radiative transfer, yeah. Also, if you want to ask your questions in person, please feel free and raise your hand. We have a question in the chat. Thanks for the nice overviews about the Wacom integration with L93. Does it mean in the near future? If so, roughly when can L93 configuration will be better to be used for modeling stratospheric volcanic aerosols?
I'll address part of that. I think the answer is yes. This L93 configuration will have full chemistry in some version. So I would expect that to be the L93 with chemistry to be the version that you would use to study volcanic aerosols. I don't know if Luisa or Nick Davis or Nick Petitella have anything to add, or Dan Marsh, and anyone.
I think that sounds right to me. I think my conception here is that CAM gets more utility for these problems and integrates a lot of Wacom functionality. But if you still want to do anything related to anything probably above the stratosphere, then you'd need to probably engage a higher top version, whatever that becomes. But I would tend to agree with Julio that that's probably the direction things are going.
Also, we can add that the L93 will have a top around 85 kilometers.
Right.
And I just as a sort of clarification of what we mean by the integration there is just that we need to be closely sort of tied in with the Wacom development with what CAM is doing, because a lot of our development sort of builds right on top of that. So that's really what we mean there by integration.
Yeah, and Simona Tilmas, she comments the L93 should be sufficient to study volcanic aerosols. Is all the chemistry in place to have the volcanic aerosols interactively simulated?
Yeah, it's already been in there. So, yeah.
Yeah, that's all part of MAM now.
Good. Again, if you have questions, feel free to raise your hand or put them into the chat. Colin, yeah, please go ahead.
Yeah, I don't want to take this on a bit of a sidetrack, but one of Julio's comments, I had a note just to bring this up regarding the kind of backwards support for things like the FE Latlon die-core and kind of some of the older physics packages. My question was mostly for either, I don't know, the co-chairs or the SSC. I mean, do we have any information on how many users actually rely on some of those configurations? I know we saw, like, Steve said there were 49 potential physics configurations or something like that. I mean, are we really holding on to some of those for, a couple scientists here, a couple scientists there? Do we have any thoughts on that?
I think that's a great comment. And part of my answer would be that we're not, if people rely on certain tags, those won't be going away. It's pushing these things forward in the development stream that I think is what we're thinking about. So I have to say I'm a little confused, frankly, by what the difference is between maintaining something on the development stream and maintaining its existence in a tag. But my understanding is that it's a lot easier to do it if that the maintenance is a lot simpler if it's maintaining a tag than it is to keep it alive in the development stream. And I see Steve is he's walking away. Sorry. I thought he was.
Steve might want to comment on that.
So the point is that when we try to put new features in or fix bugs, we have to test on all those physics configurations, because very often putting something new in will break something old if you're not careful. Or, for instance, a new feature that modifies the behavior inside of the DP coupling layer very often has to be replicated in all 5 die cores and then tested in various configurations, because some configurations use gravity waves, which we get information from the die core, and some configurations don't. So all of those turn out to matter in terms of successful running. However, an old tag, the way CESM's been configured for quite a while now, with an old tag, the only thing that really requires maintenance is the machine support, and that is all now been encased in seam. So all we have to do is update the seam external, and we have a new working old tag. So that allows us to maintain support, which is why CESM 2.1 is still a supported configuration. And what this does is it slows down our process of creating tags with new features in it, because we have to check that everything works, and then we have to fix the things that didn't work. It's quite a complex system, and we're trying to work on infrastructure that would make it more modular and require less work to make sure everything's still working, but that's a heavy lift given that we've got a large number of scientists adding new features, and we're trying to keep up with that workflow. So I hope that helps a little bit in understanding that it's new features that are going into CAM development that do not go into the old tags that cost a lot in terms of just trying to make sure it's all working before we tag it.
Yeah, I mean, I guess, like I said, I don't think we want to necessarily diverge into like a huge philosophical discussion. But to me, it seems like if that is even a moderate drag on getting new science into the model to support something like the Eulerian dicore at low resolution for paleo studies, I think we probably maybe want to do a cost benefit analysis on that, because if really you are not kind of operating at maximum efficiency to satisfy a handful of people, then I kind of agree with Julio. Maybe the option there is to sunset support in a particular tag. If you want to run everything, you got CESM-AMWG or something like that. But like I said, that it does sound like it's getting to the point where it's a problem and it's slowing down science for, it could be slowing down science for the majority of users. So yeah.
Also, before then, let me just read Brian Dobbins and put into the chat. Yeah, in addition to what Steve said, in the future, I'm hoping we can, when allowed by users, collect user statistics on comp sets, resolution, and physics, which can help inform these things. So it would be good to know, as Colin mentioned, how many people are actually using Eulerian, for example, the Eulerian dicore. Then March first, and then we have a chat question.
Yeah, I just wanted to comment that I think in general it is a good idea to start thinking about what we can sunset to limit the overhead. But I think that needs to be in close consultation with the Paleo Working Group so that we aren't isolating a certain community, and that perhaps that what they need can be picked up in something like the simpler models. But I would caution against a popularity or contest here. I mean, in reality, only 1 or 2 scientists are going to be able to run the high resolution model because it takes about 1/3 of our machine to run it. So we can't just be doing a numbers game here. We need to just make sure that we're addressing the needs of the community.
Yeah, good point. So we had a question from Hanli Liu. Are you, do you want to ask it yourself, Hanli, or I can read it?
Can you hear me?
Yep.
Oh yeah, I was just wondering from the what Nick showed. It seems that there's a symmetry problem. It's too symmetric, the stratosphere wind in the northern winter. I was wondering if there's a comparison in the southern winter and if there's a similar issue there too.
Yeah, so Dan, it's funny, I actually looked at this. I can't recall the distribution. It does look very symmetric in the southern hemisphere, but I think it should be more symmetric anyway. But there is a median wind bias there too. But we're going to look at both, try to understand what's going on. But I can't really say too much on the distribution of OBS versus Wacom in the southern hemisphere right now.
Thanks.
Yeah, we also have a little bit of discussion about, and this is for Steve, the transition to the new machine, the anchor machine, the ratio. When is this, maybe just as a general point, when is this coming online for the community?
I don't know if we have a delivery date yet.
Okay.
It was supposed to be here a while ago, I think, but there's been, a couple of supply chain issues, I guess. No machine for a while. I don't know the dates.
Yeah, Steve also mentioned there are old configurations which are clearly heavily used, for example, the CAM4 physics, and it does not make sense to sunset those. I second that actually. For community members, CAM4 is very useful.
Would a survey of some sort be helpful if we can identify the configurations we think are probably not likely used much, if at all, and circulate those in the community to get feedback on?
Yeah, I think we should entertain that idea. Yeah. We're also at time, so it's 10:20 in Boulder, and we have a 10-minute planned break. So feel free to, of course, this channel stays open, so feel free to chat more via the chat or interactively, but let's stop the official first session. Let's take a 10-minute break, and we come back in 10 minutes with the physics session. So welcome back. It's 12:30 my time. And I think the YouTube channel is starting again. Let's start our first science session. And today is mostly devoted to AMWG. The first morning session now is about physics developments. And we start with Adam Harrington from NCAR, who talks about CLUB.
Yes, thank you. Okay. Okay, you can hear me, Christian?
Yep. Take it
And
away.
you can see me? All right.
If possible, please leave a minute or so for questions at the very end. Yeah.
Okay, so I'm going to talk about the current status of CLUB-MF in CAM. This is the CPT team for CLUB-MF. PIs Joao Teixeira, Julio, and Michael White. Michael's at Naval Postgraduate Lab, and Joao is at JPL, also affiliated with Jeffresse at UCLA. And all of these folks who are very helpful in pushing the science through. So I'm going to start off, my title slide has just sort of the motivation figure. And so what you're looking at is a point in a BOMEX scam case. It's a grid point, and it shows the subgrid distribution of vertical velocity from CLUB. So you see this double camelback hump, which is that double Gaussian PDF representation of subgrid variability that CLUB gives you. The blue is in the LES solution, quote unquote, the truth that we want from George's LES out of University of Connecticut. And the idea here is that the double Gaussian PDF does not do the best job in capturing the long tail here that is the quote unquote skewness of the distribution. And that by introducing these mass flux plumes, it ends up populating that tail of the distribution that's missing in CLUB. And this isn't a schematic, this is actual data. And so you're looking at what the output actually looks like, which is a proof of concept that we think we're going in the right direction using this approach. So just a quick outline, I'll talk about some preliminaries, and then the two main results section about using SCAM to sort of calibrate marine stratocumulus to trade cumulus transitions with CLUB-MF. And then we'll take a first look at our deep convection experiments using CLUB-MF, where we've just done some simple deterministic entrainment experiments to get a handle on what type of parameters we need to get deep convection. And then the sort of work in progress, longer term goal is unifying these two regimes with the hope that we could potentially provide an alternative to using the ZM scheme for convection. And then we do have a paper that's in the review process that Michael has authored as well, looking basically at shallow convection in the SCAM runs. Just an FYI. So the main milestones in the code since I've started this work, and so Michael had developed the first iteration of the CLUB-MF code. It is an ensemble of updrafts using condensation and or having macrophysics embedded into it. It is based off of the EDMF method from many of Kai's papers over the last decade. And the way that, basically we're using CLUB to basically as the Eddy diffusivity part of the EDMF method. And so it's called CLUB-MF. And we are simultaneously solving for CLUB-MF processes using the CLUB solver. So it's more or less a unification of mass fluxes with CLUB. The first sort of big thing was just refactoring the workflow to make it more efficient to run and develop from the CAM coding perspective, numerics of solution. We had a lot of work to do there, getting the random number generator, a bunch of different stuff. And that set the basis for this sort of version 0 that that I went through a lengthy code review with the software engineers to put on the CAM trunk and introduce a regression test to protect this functionality. And the idea here was to create a stable base code that we can build off of. And so now I can say anything we introduce to the code after this point, and if it breaks the code, it's due to something we introduced after this point. And so it turned out to be a pretty prudent decision to go through this early on in the process. Next major milestone is sort of coupling the precipitation rates consistently to CAM. We use a simple microphysics parameterization right now from Kai. And one main point is at the moment, we're sort of omitting any ice phase physics from these mass flux plume because club does not live in a world where it can change ice phase. And so the thinking is, work with what you got here. And so that is a limitation at the moment. And then mass and energy conservation are sort of required if you're going to start coupling precipitation. And there's always this issue of club is one of the only physics routines in CAM that actually doesn't conserve CAM's version of energy, and so it fixes it. I'd say a tangential progress is we've actually just, this is not really to club them up, but just in general, we have made some progress on identifying the causes of club's energy imbalance. And we really think that there's a problem with the boundary condition that we have come up with a solution for. But that's for a separate discussion. Coupling the cloud ensemble to CAM radiation. And then the focus we're on right now is focusing on how we can enhance the entrainment formulation to work for multiple cloud regimes. This involves some type of dynamic calculation of the entrainment parameters. And I'll talk a little bit about how we actually are incorporating environmental turbulence to inform entrainment as well in a minute or so. So just a brief overview of the type of convection. This is called surface-driven convection. And so it's very different than the sort of typical deep convection quasi-equilibrium type schemes. We are initializing each member of the plume ensemble by backing out a convective velocity scale from the surface fluxes. So this Q star is the buoyancy flux from the host model. And that allows us to pull out temperature and humidity scales from the surface fluxes using that convective velocity scale. We can then derive shape parameters for this trivariate, sort of a trivariate Gaussian representation of the subgrid distribution at the surface based on relationships between these star quantities and shape parameters that we take from LES. You initialize this plume ensemble's vertical velocities by taking n samples, n members, and you draw it from the right-hand tail of this distribution you just constructed. And so you now have the initial conditions, and you can integrate the plume equations upwards. And this is the entrainment rate, which is important as well, and I'll talk about that in a minute. And that integrating the plume upward gives you a buoyancy at each level, so then you can solve for this approximated steady state vertical velocity equation that's typically used in shallow convection schemes, not very common in deep convection schemes. And so then the plumes will terminate when the vertical velocities go to 0. We fix the area of each plume member, but that doesn't mean that the ensemble total area is constant with height. As certain plumes die, that actually reduces the ensemble convective area, and so you do have a varying ensemble area with height. And this is just an idea of what sort of this surface-driven convection looks like in a curtain plotting gate. And it has this sort of nice convective boundary layer to shallow convection to deep convection growth evolution that we hope we can retain in the 3D simulations. This is SCAM. That's very different from the ZM type convection where it's very punchy on and off. That is, predominantly determined by its Cape closure condition. I am going to skip this in the interest of time, but it's just a schematic of what the code looks like. And I want to move on to bridging the gap from SCAM to 3D simulations. And so Julio has actually implemented a method of forcing SCAM with 3D model output or reanalysis. And so you can just pick any point on the globe and run SCAM at that point. And then SCAM will then pull the 6-hourly data that you feed into it and compute the forcing at that point. And so I've constructed 10 SCAM points along this magic region transect from Long Beach to Honolulu to try to simulate the stratocumulus to trade cumulus transitions you see in this region. And this is an example. It's the cloud low fraction averaged over JJA from SCAM versus longitude. I'm forcing SCAM with this blue line here. So this is the 3D output climatology. And the crosses are the actual SCAM solutions. And so the blue cross being forced by the blue solid line is reproducing the 3D solution fairly well in this SCAM transect. This no trap is just a change in the name list, and it ends up increasing clouds by about 0.1 across this transect. And that sensitivity is also recovered in the 3D solution, which is the increase in cloud fraction you see here. And so this is useful for reproducing sensitivity in 3D runs, provided you don't push the system so hard that the forcing is no longer representative of the system. For simulating this transition, we need to focus on the entrainment rule. And we use a sort of a newer type of entrainment rule that's given over here. And it's based on this concept of entrainment being due to a discrete number of entrainment events, and that this L term is the length scale a parcel will sort of travel before it experiences this event. And so we need to, shallow convection will have smaller length scales, and deep convection will have longer length scales. And so this is something that needs to depend on cloud regime. Right now, we draw these events from a Poisson distribution where L sets the mean or the shape of that Poisson distribution. And so here's a parameter sweep in L for club MF. And when I use a large L, so 50 meters, what happens is that you don't have any more stratocumulus clouds, they disappear. And they go away because the entrainment rate at large L is now so small that these plumes will then penetrate through the inversion layer and mix free troposphere air right into the stratocumulus decks. And so it enhances this cloud top entrainment and destroys the stratocumulus clouds. And so you need to probably have a smaller value of L. Say out here, we're on the order of 10 meters and we're getting some realistic stratocumulus decks by allowing those plumes not to interfere with what club is basically doing, which is generating this nice stratocumulus decks. And then out here in the trade cumulus region where things are more amenable to what the mass fluxes represent, we can have sort of more reasonable length scales that are associated with this sort of shallow convection type going on here. So, oh gosh, I only have a few minutes. But I want to just talk quickly about this TKE enhanced entrainment. So there's an idea that Joao has come up with that, usual entrainment is determined by plume generated turbulence. That's how we parameterize it usually, where your entrainment rate is proportional to the mass flux. But we have experimented with also considering environmental turbulence that the plume is in contact with. And so a plume here going through a turbulent environment would experience enhanced entrainment. And we think this is both physical, and it also really helps to partition the work between club MF, where club is generating a lot of turbulence. We can let club do its thing. Where it's not, we can let mass fluxes do its thing. And so these crosses here are simulations with fixed L from 10, 20, and 30 meters. And then the circles are the same experiments, but I turn on this TKE enhancement. And what it has the effect of basically backing off where there's these stratocumulus clouds, and you get a nice transition from stratocumulus to stratocumulus.
So Adam, we need to wrap up here.
Okay. So I just want to show some 3D results quickly. basically, this is also transferring into the 3D results we see in AMIPS. This is ClubMF's clouds, and this is just Club Alone's clouds. And then the turbulent fluxes, I guess we can just pay attention to this component over here. This is the mass flux only component of the turbulent fluxes in ClubMF. And as you go away from Long Beach into higher SST regions, you now start getting more mass fluxes are more active in the cumulus regions, and that's desirable for what we're trying to compute. Deep convection, we just started looking at this, and I don't have time to say anything because of the time constraints, but I will just say that we are getting realistic deep convection with ClubMF. And so we now are at the stage where we seem to be able to compute both cloud regimes, shallow convection and deep convection. And so we need to, we are focusing on unifying this entrainment rule for all cloud regimes. And that's the primary takeaway of this talk is that. So I'll stop there.
Thanks, Adam. Very interesting. We are out of time, so any question that might arise, I would like to push to the discussion. Our next speaker is Colin Zazicki, and he also talks about Club.
All right. How does that look? Or do I need to flip the displays?
No, looks good.
Perfect. Okay, so yeah, following up on Adam's kind of kickoff to this CPT session, I want to talk a little bit about some of the optimization we've been doing in Club with a particular emphasis on looking at sea level pressure patterns. So, you know, so this is a CPT that's jointly funded by NSF and NOAA, and we're explicitly interested in momentum processes within the boundary layer. So I keep showing this one slide overview, but this is the team that's been working on this problem over the past couple of years. I just want to highlight that both Kyle and Joachim are going to be giving talks during AMWG. Kyle is coming up later today, and Joachim's on Wednesday morning. So stay tuned for some more interesting research. This is just kind of the one slider of what we have been working on. So we really have two main thrusts to this project, two main improvements within Club. So the first is to directly prognose momentum flux evolution in Club. So rather than using just a Eddy diffusivity formulation, actually predicting all of the source and sink terms with regard to vertical momentum flux in the boundary layer. So U prime, W prime, V prime, W prime. And then the other component of this is defining what we refer to as a regime-specific Eddy timescale formulation. And what this kind of allows us to have is a little more control over the turbulent dissipation in different regimes. So we're not kind of applying a one-size-fits-all, you know, kind of diffusive profile in stable boundary layers versus kind of highly sheared flow, but allowing kind of the shape of that profile to vary as a function of kind of what the stability and what the regime in and of itself is. I don't want to get too into the weeds with equations. We have a couple papers that have kind of talked about the basic frameworks of these kind of improvements. So one thing I want to talk a little bit about today is this kind of what we refer to as this TAUS formulation and an optimization using this TAUS formulation. And this TAUS formulation is this equation down here, which is meant to give us, again, kind of more physical control over what turbulence is doing in the boundary layer. And it's worth noting that, you know, the idea is we don't want to just add more tunable parameters to Club. Really what we want to do is kind of provide a more interpretable, from a process-oriented standpoint, kind of control over the momentum fluxes in Club. So it's worth noting that the way that, and this was originally published in Guo et al. 2021, but the way that this has kind of been designed is that we've added these kind of additional controls on the dissipation within the column. But in doing so, we've removed some of the kind of tunable parameters as well, such that really all we're doing is we're kind of trading tunable parameters. We're not adding additional degrees of freedom to the tunable parameter set that is currently in CAM. And so what I kind of wanted to talk a little bit about today is some kind of really I would say, work in progress type stuff. So this is kind of one of those projects that I started on a whim some, I don't know, late some Tuesday night instead of grading or something like that, that I was like, oh, this will be a fun half an hour project. And now I've been kind of working on it for a couple months. But the idea is that we use this kind of algorithmic optimization technique, and we're using the one of Nelder and Mead. It's actually a fairly old one, 1965. Sometimes it's referred to as the downhill simplex technique. It has been used in climate models before. There are a few papers in publications. And it's also not the only optimization strategy. So things like Markov chain, Monte Carlo, simulated annealing have also been used in the past. What we refer to as an optimization strategy, I suppose I should back up a step. But this is essentially a mathematical technique for taking a model with multiple kind of tunable parameters, multiple inputs, and trying to optimize those multiple parameters for a potential target. So for example, if you have some penalty function or loss function or something like that, essentially what we're trying to do is minimize that through this kind of iterative process. And so why, could this potentially be an interesting option for us to explore when we're looking at this with Club is, for one pro is it's actually very cheap in the grand scheme of things. I mean, if you're talking about Monte Carlo methods, these tend to involve thousands of simulations. It can get very expensive. It's fairly easy to code. I was actually able to code this up, like I said, in a couple hours one night. But what's most interesting to me is it provides really followable paths. So this is an example of what an optimization kind of path would look for. This is just optimizing a two-dimensional function known as the Rosenbrock function, where the local minimum is kind of right here. And you can actually follow kind of the way that this algorithm is trying to reach that local minimum and kind of infer some of what it is prioritizing as it moves from A to B. Some of the cons, it's not an algorithm that has true convergence, and it also can struggle in situations with multiple local minima. But I would argue when we're thinking about CAM or a climate model, there is not really something known as true convergence. I suppose maybe if you were looking at like an analytical test case and a die core, yes. But with a coupled climate simulation, you're not really looking for some sort of perfect convergence, some perfect answer. But really what we're looking for is an answer that is as closely tied to the physical atmosphere as possible. So this is just kind of a quick proof of concept that we've done. And essentially what we do is we run an out-of-the-box CAM6 simulation for a short period of time, just a couple days. And what we then do is we kind of hide the values of C14 and CK10 from the model. Now the default version, the default coefficients in CAM6 are 1.6 and 0.5. And what we do is we say, okay, well, we're going to apply this optimization. You're not going to know what the right answer is, but I'm going to let you minimize the error in the zonal wind below 700 millibars, let's say, between any given run and what this reference run is. And there's a couple other techniques that we use. We can use like a pre-run screen and a penalty function to constrain the model configurations. That's not overly important. But what's important here is that what we do is we run these successive 2-day hindcasts, adjusting C14 and CK10, and this piece of code eventually, without any user input, will converge on the right answer. And it takes about 50 simulations to get there, which is about 100 model days. So this is actually relatively, quote unquote, cheap in the grand scheme of tuning a parameterization. So our hypothesis for using this kind of experimental version of Club that I highlighted earlier is better representation of low-level dissipation will improve both the sea level pressure fields and the surface stress fields. These have been kind of an issue, I would say, since Club has been brought online between CAM5 and CAM6. Historically, we've been able to get better sea level pressure fields in climatology. It comes at the expense of worse surface stress fields and vice versa. Usually CK10 has been the parameter that we've experimented with that. And what we're going to do is just run a 2-step optimization procedure. So the first step, what we're going to do is we're going to nudge the full atmosphere to ERA 5. We're going to run a 10-day hindcast. And what we're going to do is we're going to try to minimize the global mean nudging tendency. So by minimizing the global mean nudging tendency, what we're essentially trying to do is we want the solution to be as closely related to the observational evolution as possible, so ERA 5. And then we're going to have step 2, which I'll talk about in a couple minutes. But essentially what we're going to do is use the settings we learned in step 1. We're going to turn off the nudging. We're going to run these 2-day hindcasts. And what we're going to do is target some sort of weighted function that combines bias and correlation of shortwave cloud forcing in this newer version from the default CAM6 version. And these are just some of the parameters that kind of get spit out of this optimized tuning algorithm. I won't really get into, don't have time to get into the nitty-gritty details. So these are just numbers that are going into the machine, let's say. But let's see what this actually gives us, because effectively what we're doing is we're trying to minimize this nudging term. So we're trying to make the evolution of CAM match the short-term evolution of ERA 5, which is highly constrained by observations near the surface. So this is just looking at sea level pressure. Here's your CAM6 default climatology. This is right out of the AMWG diagnostics package for those of you who are familiar with it. This is the MERA sea level pressure climatology, and this is the error. So just the difference between CAM6 and MERA. And then here's the optimized version using the new version of Club that we've put in with this Nelder-Mead algorithm. And what you see is that if we look at the error associated with the CAM6 default and the error associated with this new version, we get this reduction in error. Essentially, we kind of increase the pressure at these high latitude regions, which corrects a bias. And we also decrease the pressure kind of in more of mid latitudes and low latitudes, which also offsets this bias here, such that our kind of diagnostic is improved. So that's a good sign. But as I mentioned earlier, one of the problems we've had with Club in the past is we can improve sea level pressure, but then we degrade surface stress. What we also find is if we look at the surface stress climatology with this new version, here's our error with the default version on the left, kind of the difference between the new or this experimental version and the default version, and then the error on the right. And what we see is, well, we don't really completely get rid of, for example, this high bias in the southern storm track. We do mitigate that with kind of this optimized tuning. So at least from a mean climatological perspective, we have been able to improve both the sea level pressure patterns and the surface stress patterns combined with this updated version of Club. And then the last kind of thing I want to talk about, I guess, is this idea of interpretability. So this is kind of one of the things I've been really interested in, is we can do these optimizations in a black box, but we kind of want to learn why they're doing what they're doing. So what we can do is we can define this quantity known as the effective Eddy diffusivity. Really, just when you have prognostic momentum, you don't have a real Eddy diffusivity coefficient, but you can kind of back it out by looking at the momentum fluxes and the shear terms. And what we can then do is we can go around the globe and the climatology and see kind of how this optimization changes the diffusivity profile in CAM6. And what we find is that over many oceanic regions, this improvement seems to be a result of kind of modulating the shape of the diffusivity profile, so increasing diffusivity close to the surface, but then reducing the diffusivity kind of aloft once we get above 1 kilometer or so. But this isn't constant all over the globe. So for example, at really high latitudes, the algorithm really just wants to increase the diffusivity kind of throughout the column, perhaps telling us something more about stable boundary layers. And then kind of over, for example, the central United States, we get kind of this kick out of the diffusivity close to the surface, but we don't get kind of this flipping, this offset, this reapportionment like we do over the oceans. And I literally just made these plots this morning. So I want to limit the interpretation to that. And then I guess the last thing I'll hit on super quickly, because it looks like I'm kind of running low on time. So I mentioned a step 2 in there, which had to do with shortwave cloud forcing. And I've really just talked about momentum parameters. So the question is, why did we have to do a step 2 in this optimization? Well, if we only touch the momentum parameters, our global cloud fraction jumps by about 10%. So things like our shortwave cloud forcing score and RESTOM and things like that suffered. So by doing a second kind of iteration or a second optimization to recover the club or recover the clouds, we're able to get kind of a reasonable climatology with this Club X. It's not perfect. If we just look at the biases, for example, there are some improvements, some degradations. But what's most interesting to me, at least so far, is that if we look at the spatial correlations between a variety of all the AMWG diagnostic fields, that we see a lot of improvement over here with kind of some of this new formulation of club and this new optimization. I've highlighted our target season here in these columns. There's a lot to chew on here, but I think there is some potential in kind of using these methods to improve kind of the simulation across a lot of metrics. Some quick caveats. Like I said, there's no requirement that this needs to converge on a single best solution. One big thing we're going to have to wrestle with is multi-metric frameworks are tricky. We've only performed this with the L32, not the L58, as Julio mentioned earlier. I don't want to waste any time on that. So the big take homes. So CAM6 with prognostic momentum fluxes with this club X kind of behaves reasonably at first blush. That's a good sign as far as kind of getting this implemented within CAM. We've been able to demonstrate joint improvement of sea level pressure and surface stress climatology with this formulation and with optimization. Early indications are CAM6 is under diffusive near the surface, over diffusive aloft in many oceanic regions, which may be the source of a lot of the biases we've been seeing in terms of the pressure and surface stress. And then this optimization produces a club configuration that improves on many AMWG global diagnostics with all the caveats in the previous slide. So with that, I'll wrap up.
Thanks, Colin. Very interesting. We have a very quick comment, a question here from Julio, but also we then push further questions into the discussion. So Julio says, what does the Hindcast mean in the context of a nudged run?
Yeah, so they're kind of the same thing. So essentially we are initializing with observed meteorology, but then as that simulation is evolving, we are not allowing it to be free and only an initial value problem. So a way to think about initialization plus nudging is it's kind of both an initial value problem, but if you treat the nudging as kind of a boundary condition, then essentially what you're doing is you're saying, I'm allowing you to evolve, but not too far away from the state that we want to be. But that's a good question.
Right. Thanks.
Thanks. Let's move on. And next talk is by Kyle Nardi, who works with Colin Zazicki, and it's continuing the discussion of the sensitivity to the parameters.
All right, thank you. So I'll just note that this work is funded through the Momentum CPT, as Colin mentioned. So what I'll discuss here today is several results from sensitivity analyses where we've explored the influence of certain tunable club input parameters on both idealized tropical cyclone forecasts and then more recently global simulations of CAM6. So one of the main motivations for my work is that we're interested in improving CAM6's depiction of tropical cyclones and specifically tropical cyclone structure. So one of the first key questions is, do certain club input parameters have a greater influence on tropical cyclone structure in CAM6 than others? And we're specifically interested in exploring club because previous studies have shown that the choice of boundary layer parameterization has an influence on model tropical cyclone structure and tropical cyclone forecasts in general. So then if we can find certain club input parameters that have a greater influence on tropical cyclone structure, we can then ask the question whether or not these input parameters also have an influence on other aspects of the global climate, and if we can address other biases that CAM6 has in the global simulations. And as Colin mentioned in the previous talk, we're using a modified version of club with prognostic momentum flux as opposed to the diagnostic A diffusivity formulation, and also this regime-specific formulation of the turbulent length scale through the diagnosis of the Eddy turnover timescale tau. And I'll go into a little bit more detail about these two modifications. So as Colin showed in the previous talk, this is the prognostic momentum flux formulation. And on the right-hand side, there are various terms for the advection of momentum flux. We also have turbulent production and then buoyant production. And then importantly, we have this return to isotropy adjustment term, which I'll mention in a minute, which effectively reduces the magnitude of momentum flux. And then we have this term representing other dissipating processes. And the advantage of using this prognostic momentum flux formulation is that we're able to account for upgradient fluxes. And we also have certain tunable parameters. So C6, C7, and CU shear appear in this formulation. And they're all tunable parameters in club. We could potentially modify those and see what we get in the model output. And then importantly, this return to isotropy term has this Eddy turnover timescale tau in the denominator. And this new regime-specific formulation of the vertical turbulent length scale allows us to potentially tune this tau term. And through tuning this tau term, we could influence modeled momentum flux within the boundary layer. So then this Eddy turnover timescale formulation works by defining the turbulent length scale in terms of the product of the Eddy turnover timescale and square root of TKE. And then the Eddy timescale is formulated as the sum of dissipating processes. And we're specifically formulating it in terms of inverse tau. So if this sum here on the right-hand side is greater, we're going to have a greater value of inverse tau, and as a result, less of a vertical turbulent length scale. And physically, this represents the breakup of larger turbulent eddies into smaller turbulent eddies. So each of the terms on the right-hand side represents something different physically. So the first term is just a background eddy dissipation that's constant, it's applied at all levels. And then we have eddy dissipation due to surface effects, for instance, friction. And then we have eddy dissipation in sheared flow, which for tropical cyclones is very important because that's an area where we have high vertical wind shear typically. And then also eddy dissipation in a stably stratified environment. And an advantage of this formulation is that these coefficients, these C coefficients, as Colin mentioned in the previous talk, are all tunable within Club, and we could potentially have a tailoring of this turbulent eddy dissipation formulation based on a specific atmospheric regime, for instance, an area with a stable boundary layer or high vertical wind shear, for instance, with tropical cyclones. So we first wanted to get a sense of the baseline biases in CAM6 with this modified version of Club, specifically for tropical cyclones and the eddy diffusivity profile. So this is the eddy diffusivity. CAM6 is in blue. CM1, which we'll use as a baseline, is in orange. And at the radius of maximum wind, what we note is that CAM6 has an effective diffusivity within the tropical cyclone that is 3 to 4 times higher than that of CM1. So by default, the out-of-the-box default input parameter settings for this modified version of Club produces a boundary layer that's just much too diffusive within the tropical cyclone. And as a result, we get biases in the modeled height of maximum wind. Actually, the jet height is 1 to 2 kilometers too high compared to observations, which are shown in gray, and then CM1. And this is just one of several biases that we found with this default configuration. And we're using an idealized 25 kilometer RC-like configuration. So there are various baseline biases in tropical cyclone forecasts with this modified version of Club. And what we're interested in exploring is how can we potentially reduce some of these biases, for instance, in the jet height, which I'll focus on in this talk. So then the question is, how can Club be adjusted to remove some of these biases in tropical cyclone structure? And one of the big problems is that Club contains many tunable parameters that could potentially be adjusted. And we need to figure out a way to efficiently screen a large number of input parameters to identify those that merit additional analysis. So to do that, we use a sensitivity analysis called the Morris one at a time or MOAT method. And the way it works is that we first start with a set of tunable input parameters in Club that we wish to explore. And then we run the model multiple times, each time with unique combinations of input parameter values. And the key is that from one run to the next, we change the value of only one particular input parameter. And what that allows us to do is to analyze the difference in model output between consecutive runs, knowing that the only thing we changed was the value of that one particular input parameter. So from this, we get a sense of the influence of changing that particular input parameter on model output, for instance, jet height for a tropical cyclone. And we can repeat this with different initial combinations of input parameter values to get a sense of the sensitivity of a particular input parameter's influence based on the background state with the different values of the input parameters around it. So for tropical cyclones, we found that there were several input parameters that really stood out as being broadly influential for tropical cyclone structure in terms of the jet height, but also other aspects such as surface fluxes, radius of maximum wind, surface inflow angle, and other aspects. The first term is the CUU shear term. So this appears in the prognostic momentum flux budget, and it effectively offsets the turbulent production of momentum flux by updrafts and downdrafts. So when this term here is greater, this turbulent production term is going to be lower, and we're going to effectively reduce the magnitude of momentum flux. C surface is a weighting term in this inverse tau eddy dissipation formulation. So it represents eddy dissipation near the surface. So when C surface is higher, and we're close to the surface, we're going to get an increase in eddy dissipation and a reduction in the vertical turbulent length scale. And C shear similarly is tied to eddy dissipation, this time from vertical wind shear, which again is influential in a tropical cyclone, has high vertical wind shear. And when we increase this term in the presence of vertical wind shear, we're going to get a reduction in the turbulent length scale. So these are 3 input parameters we found to be broadly influential. They had a large average response in, for instance, jet height, but also a consistent directional response. We were confident in the direction in which the jet height would move when we change these particular input parameters. So this is just another illustration of what the diffusivity profile looks like when we change one of these particular input parameters. So we chose to perturb C shear, so that's the dissipation term in the presence of vertical wind shear. And we look at the effective eddy diffusivity and the turbulent length scale. And the default setting is shown in brown. And as we increase this input parameter, we are increasing turbulent eddy dissipation, leading to smaller eddies and then less diffusivity. And as a result, we're also getting a reduction in the height of maximum wind, and we're getting closer to CM1 in observations. So this is an example of the Morse analysis identifying an influential input parameter, and then we can make targeted perturbations to that input parameter to reduce biases in jet height in this case. And I just want to caution that this is just an illustrative purpose. We're not necessarily advocating for this one particular input parameter, C shear. There are likely multiple pathways, and it's the best solution is likely changing multiple input parameters. But this is just an illustration of what the Morse analysis tells us and using that information to potentially reduce biases. So really the next big question is, how do these influential input parameters for tropical cyclones then influence globally averaged CAM6 output? Because if we can improve tropical cyclones, but then degrade the rest of the global mean climate, we don't really get much additional benefit. So to explore this, we repeat the Morse analysis, but now we do global CAM6 simulations. Just simple 1 degree global hindcasts where we're initializing with GFS data. And for the purpose of this talk, I'll just show one initialization from December 1st, 2019. And I'll note that we're using an updated version of Club in comparison to the version we used for the tropical cyclone work. But it still has prognostic momentum. It still has the regime-specific eddy dissipation formulation. But there are several input parameters that were eliminated in this version of Club that we had used for the tropical cyclone simulations. So those are removed from our analysis, and we also add some additional input parameters we wish to explore. And we also have some new default input parameter values, which, if I have time at the end, I'll show has given us some difficulties in terms of determining what the appropriate bounds of perturbing these input parameters are and trying to get the right combination of values. So this is an example of the sensitivity of globally average 10-meter wind speed for each of these input parameters. So this is 13 different input parameters, each denoted by a unique letter and color identifier. And this is for plus 24-hour simulations of globally average 10-meter wind speed. And for parameters that are closer to the right side on this left plot, they produce a larger average response in 10-meter wind speed. And then for those closer to the top, they produce a larger nonlinear response in 10-meter wind speed. So ideally, we're looking for input parameters that are closer to this right side here. That shows that when we change those input parameters, we are getting a larger average response in 10-meter wind speed, which is what we desire. Now, this is a plot of monotonicity, and it's asking the question, how often does increasing the input parameter increase the global 10-meter wind speed? For parameters close to the top, when we increase the parameter, we're frequently increasing the wind speed. And for parameters close to the bottom, we are frequently decreasing the wind speed. And I'll highlight here the 3 input parameters that I highlighted as being influential for tropical cyclones. And what we see is that they are also influential for the globally average 10-meter wind speed. And importantly, they produce consistent directional responses. So either frequently increasing the 10-meter wind speed or frequently decreasing the 10-meter wind speed. So that was a globally average perspective, but we can also look at the sensitivities at each individual grid cell in the domain. And what we see is that there's actually a regionality and spatial differences in the sensitivities that we see. So on this left plot, the darker colors imply there's a larger average response in 10-meter wind speed in that particular region. And the brighter colors indicate that there's less of a response. So this indicates that it's probably better to be looking at a grid cell by grid cell analysis of these sensitivities rather than just painting a broad brush of globally averaged quantities. And one main reason this is important is that a lot of these input parameters we're perturbing, again, are tied to the background atmospheric regime. In this case, this is the response to that C shear term. So we expect that this shear term is going to be more influential where we have higher vertical wind shear. And that's exactly what we see here. So again, these are kind of messy results here because we're just looking at one particular initialization. So if we were to eventually go over a number of different initializations, we'd have smoother results. But in this case here, we can actually see the different extratropical cyclones that are shown in this one model initialization. But what we see, for instance, over Greenland, we have a high value of vertical wind shear, and that's collocated with a high average response in this shear term. So this again indicates that these regime-specific formulations of the turbulent length scale could allow us to potentially tailor the value of, for instance, the shear term to a specific atmospheric regime, maybe where there's higher vertical wind shear. Now, the last thing I'll show here is, as I mentioned before, we're having some issues with determining what the proper values of these input parameters actually should be. It's still a little bit of a black box. It's one of the reasons why we're exploring some of these global simulations is to get a sense of what some of the better combinations are. And what we're finding is that for certain combinations of input parameter values, we're getting some instabilities after about 36 to 48 hours. And we're interested in exploring why that is the case. So these are vertical profiles of eddy time scale. So this is that tau term. If we have higher values, we're having larger turbulent eddies at the particular vertical level. And this is for 12 hours. So this is at a point where all of the runs are still stable, but the ones that are in orange crash about 24 to 36 hours later. And what we're finding is that all of these unstable configurations have high values of eddy time scale, either throughout the free troposphere as shown here, or for these profiles, it spikes closer to the surface. We think that might be something to do with that sea surface term, which would only really be influential closer to the surface. But we're finding that some of these combinations of low values of the inverse tau coefficient, so low values of eddy dissipation, potentially could be producing some of these instabilities. That's something we're still actively exploring. And one thing we're going to try to do is to reduce perhaps some of these bounds to make sure we have combinations that are stable. So with that, I'd like to thank our partners in this work. Again, this was funded through the Momentum CPT. If you want more information about the tropical cyclone aspect of this work, I'll refer you to this paper that was just accepted in Monthly Weather Review. And it's my contact information here. I think I'm right at 15 minutes. I'll leave my main takeaways up. And if there are any questions now, happy to take them. Otherwise, we can answer some questions in the discussion later.
Thanks, Kyle. It's very, very interesting. Are there any questions? Don't see any. I have one which I can ask now. Maybe you mentioned, but I didn't see it. What was the resolution that you assessed, and what are the implications or the results? Are they general? Do you think they apply to different resolutions as well?
So for the tropical cyclones, we were looking at a 25-kilometer horizontal grid spacing over 56 vertical levels. And then for the global simulations, it was just 32 vertical levels and just 1 degree simulation. That's a good question. One thing we do want to explore is eventually using like a variable resolution mesh, for instance, over a particular region, seeing if that does have an influence. We haven't specifically looked at how for instance, for tropical cyclones, how it would change with horizontal grid spacing. That's a good question.
I don't see any more chat questions. So again, if you have questions, we push them now into the discussion period. And our final speaker of the session is João Teixeira, and he also talks about boundary layer physics.
Hello, can you hear me?
Yeah.
So can you see my screen?
Yes.
So let me know if I am speaking to a slide that you don't see because my connection. So thank you for the opportunity again. I will briefly do an overview of the CPT that is essentially about unifying the boundary layer and convection parameterization. And it has all of these participants. I'm the main PI, but Julio, Leo, Rongfu, George Mateo, and Michael White are also PIs, and Adam in particular is the key person at NCAR doing all this amazing work that he just talked about. So let me go to the next slide, and again, let me know if if there are issues. So let me first of all highlight the fact that the main goal of the CPT and a lot of the work that we are performing and other groups as well is to try to get away from this artificial modularity that exists in weather and climate models in the atmosphere, as well as in the ocean, but we're talking about the atmosphere. And the figure I have here is a figure that highlights often how, in a way, are naturally unified. I mean, the deep convection, shallow convection, boundary layer, turbulence are all sort of manifestations of fluid dynamics and thermodynamics. But in our models, the way to parameterize these different aspects is often very modular. And it's modular in different ways. Each model does things its own way, but often models will have, you know, a parameterization that does stable boundary layer, a different one that does dry convective boundary layer. Sometimes have a separate one for stratocumulus, and shallow convection is in a completely different place, and then cloud microphysics and macrophysics are dealt in a completely different place. And our goal is really to sort of come up with a way to unify the parameterizations of boundary layer and convection mixing and have a routine or a set of routines that in sort of a both, you know, algorithmic and code-wise are unified in trying to sort of reproduce these different manifestations of turbulence and convection. And so the work that we have been doing over the last several years is based on an approach called the Eddy diffusivity mass flux approach, EDMF. And I just have a very quick slide here. The key aspect of much of the stuff that we've been doing, and a lot of this is in several papers authored by Kai Susha and a lot of us in the team, is this idea of using not only the Eddy diffusivity and mass flux are coupled to each other from the beginning, from again the algorithmic and the code level, but that we also introduce this idea of multiple plumes, and then these plumes will have sort of a life of their own, so to speak, in which they after the parameterization of surface layer thermodynamics, we sample from those PDFs to produce multiple plumes that will be, some of them more energetic from the beginning, others less, and they will also face stochastic entraining events that are parameterized in the way that Adam mentioned, that's sort of inspired by Romson Kwang. And is this combination of a parameterization to represent sort of more the smaller scale processes like eddy diffusivity with the multiple plumes to represent convection and sort of structures that exist from, let's say, the subcloud layer to the full troposphere, that is sort of at the essence of what we do. And one of the things, before I show some results from both GFDL and mostly from NCAR, one of the key aspects, as everyone knows, sorry, this is going too fast. One of the key aspects, one of the key tools, or I would say the most fundamental tool that we have used and all of the groups that are developing parameterizations use is large eddy simulations. I'm not going to expand on that because you all know what large eddy simulation models are. But I just want to give you two examples of some of the remarkable work that is being done under the CPT, mostly by George Matteo and his team at the University of Connecticut. The top figure is, this is the development of convection from shallow to deep over land. This is based on a field experiment in Africa. And these are the last 4 hours of the LES simulation. And you can see that this is cloud water path. And you can see how the structures, you see the domain, this is at the top. You can see the domain is about 80 by 80 kilometers. And you see that around 3 o'clock, let's say in the afternoon, you will have sort of shallow convection. And then about 3 to 4 hours later, you have these much larger structures that you would expect. One of the most important results that George Matteo and his team have obtained, and they wrote a paper they submitted recently, is the dependence of convection organization on the domain size. And these are 3 images of exactly the same case of convection. So the LES is forced exactly the same way, except that in the bottom left, you have a domain of the LES just 40 by 40 kilometers. The middle domain is 80 by 80, and the other one is 160 by 160. And what you can see is that in the 160 by 160 kilometer domain, you have convective structures that organize themselves and that have scales that are way larger than the 40 by 40 size of the first domain, but also extremely complex. And a lot of the results that they have there have a very significant potential impact on parameterization development. One of them being the fact that although the structures do look very different and in many sort of morphological aspects are very different, a lot of the fundamental variables like the vertical mixing is actually relatively similar, which in a way is sort of encouraging for parameterization development. Let me just show you then a couple of results. The first one, so we have slightly different, well, slightly, we have different paths in terms of what we are doing with the GFDL team versus what we're doing with the NCAR team. At GFDL, the approach was to first implement a turbulent kinetic energy eddy diffusivity mixing parameterization, the MYNN. That was done, and this is a lot of work by the team at GFDL. This is just one example of some results from a few months ago. On the left, you have low cloud cover from the GFDL control. On the right, you have it from the new model. The new model is a little bit better, as you can see in the stratocumulus regions. You can also see it along this GPCI Pacific cross section from California to the IDCZ. And I'll show another slide about the NCAR results there as well. And you can see again that on the left, the control version seems to have less clouds than on the right. Now, although these results are encouraging, there were several issues with this version, particularly in terms of when we did the long-term sort of 200-year couple runs in terms of balance, radiation balance at the top of the atmosphere, which is very difficult to get and very difficult to compete with the control run, which has been highly calibrated. And right now, the work is that at GFDL, the team is investing a lot on coupling the eddy diffusivity with the mass flux, the multiple plumes, and also coupling to the Titka cloud scheme, which is a challenging cloud parameterization scheme to couple to. And I could say a few words about that later on if you wish. Now let me focus the next few minutes, so the last few minutes, on the NCAR results. So Adam just talked about most of what is important of the great stuff that he and the team is doing with the NCAR model. A couple of things to highlight. One of them is the fact that we actually, and this is something we do with EDMF, and in this case we do it with ClubMF from the beginning, which is that we try to couple these parameterizations at sort of the core level, which is at the algorithm, at the solver. And Club has a 5-diagonal prognostic solver for both the mean fields and the turbulent fluxes, and that's where the mass flux plumes are integrated, merged into. And all of this is solved simultaneously, so which means that the mean fields and the turbulent fluxes, supposedly turbulent fluxes at the smaller scale, given that the larger scale is given produced by the mass flux. They are aware of the mass flux, and mass flux is aware of it as well, while this is solved simultaneously. Let me just show you just a couple of results. The first one, this is an analysis that is done in Michael White's paper that, as Adam said, the paper was submitted last fall and has been revised and in the process of second revisions. Hopefully it won't be a long process, but this is just one example of the analysis that the team performed. Essentially, the idea was to look at a single column model with Club plus MF and versus Club versus LES and analyze both shallow convection over the ocean and over land. This is just one example. BOMEX is shallow convection over the ocean. You can see both the liquid water and cloud cover to the right, the LES in black, and then just focus on the blue line and the red orangey line. The blue line is Club, the orangey red line is Club plus MF, and you can see that Club plus MF is able to produce more realistic cloud cover and liquid water and closer to the LES. And essentially, and this can be seen in the paper in a complex analysis that is done to the turbulent fluxes and all that, you can see that what happens is that the mass flux plumes do provide additional vertical mixing to Club that allows the model to reproduce convection better, shallow convection. And just one way of sort of illustrating that is by plotting joint PDFs, both from the LES, the Club, and then the location of MF discrete plumes in this sort of phase space of temperature and water. And what you can see, this is in about 250 meters above cloud base. So a lot of very active convection is going on. And what you can see is that these discrete plumes do populate a skewed part of the PDF that LES clearly shows that the Club itself is not able to populate that. Either work conjointly with MF or even Club alone is not able to go into those more sort of far-reaching regions of skewness. And in that sense, that's what the plumes are doing. They're reproducing a very difficult area of the PDF of thermodynamic properties and producing more efficient mixing. The last slide I have before the summary is a slide that is, these are just that Adam also showed in his second to last slide, I think. So the challenge right now is for us to actually have three-dimensional runs using this particular version that are able to not only reproduce shallow convection and dry convection, which we already showed we can do well, but also stratocumulus and the transition to cumulus, and hopefully not far from now deep convection as well. And here you can see this is the magic GPCI transection, Pacific cross section. This is the one in the bottom is just the magic one, which is essentially a straight line. Well, not a straight line, but a line between Long Beach and Honolulu. And at the top left, you have the club results for cloud cover, cloud fraction, and the top right is club plus MF, and the bottom are two sort of incarnations of satellite observations. And you can see that both club and club plus MF actually reproduce the transition in a very realistic manner. Maybe club plus MF has a little bit more clouds in the stratocumulus regions, and in transition as well, which seems to match potentially the observations a little bit better, but that's actually not clear at all. So I think they're both relatively robust. And so that's very promising. My last slide is a summary. We feel, not only us, but others as well, of course, that there is an urgent need to develop and implement unified boundary layer and convection parameterization. It's a way to avoid modularity, which modularity in weather prediction models may not be so bad in the sense that what you want is to get, to know if it's going to rain in 5 days in London or not. But when you want to try to be able to represent very subtle differences in sort of the net top of the atmosphere radiation balance, then it's not particularly ingenious to have all this artificial modularity and combining things in a sort of more of an engineering manner. So the CPT project, we have created more sophisticated LES setups and case studies. We're going to continue to do so. We've implemented Eddy diffusivity TKE in the GFDL model, and now the challenge is actually combining the EDMF that is now implemented with the TITCA cloud scheme. We produce, ClubMF produces more realistic shallow convection in SCAM, both over ocean and land. That's the Michael White paper. Results that I showed in Adam as well, that ClubMF produces realistic stratocumulus to cumulus transitions, and it started to produce realistic. The goal is really in the next 2 years to develop and implement and validate and hopefully deliver a fully unified PBL plus shallow plus deep convection ClubMF in CAM. So thank you for your time.
Thanks, Zhao. Very interesting. Are there any questions? There are a couple of more general comments about PBL schemes in the chat, but let me ask Zhao, are these simulations already done with the L58 configuration?
They are. So these are the L58 simulations.
Okay. I wondered.
Can you still see it?
Yes.
Yeah, they are L58. You can see it.
Okay. Yeah. I just wondered on your slide 9 on this one. It seems that club cuts off the turbulence at 2,000 meters and observations carried on to maybe 3,000 meters. Is this a feature?
No, this is. I don't think I would worry too much about that. I think that from the experience I have of looking at these results both from club and club plus MF with L58 are very impressive in their own. Adam in his slide also had the Vocals cross section, which was quite impressive as well. The satellite observations do go a little bit deeper.
Mm-hmm.
I don't know how significant and meaningful that is. It may be a little bit, but just getting to the point where we are right now with L58, I think that's very encouraging from a PBL clouds perspective.
So again, if you have questions for Zhao, we can address them now. And also, I want to open up the floor for general questions about PBL. Kind of all the 4 talks we heard.
I'll just add to Joao that looking at the turbulent fluxes, they seem to be more extensive vertically than this cloud fraction metric, which is it is what it is.
Adam, do you want to comment on the chat? You were involved in the chat questions here.
Oh, I was talking mostly with Colin about moving to L58, so similar theme to what you were talking about. I just think, at least with Club MF, we found that changing the boundary layer resolution does have a substantial impact on the solution, and so you know, doing everything at L32 and then in a year or so everything's changing underneath you to L58 is a potential collision course. So I was just recommending to be active in moving to L58 sooner rather than later.
Yeah, and I think Adam brings up a good point there. So one thing that Kyle actually found that was quite interesting is that at least in tropical cyclones, a lot of our metrics that we were using, profile, mass flux across isobars, things like that, were relatively insensitive to vertical resolution. But that said, tropical cyclones are a very specific kind of dynamical phenomenon. And it wouldn't surprise me if we had more sensitivities going from L32 to L58 in the global simulations. So I think that actually is something that's kind of an interesting question in and of itself, is where is that vertical resolution going to matter? And that's, I guess, one question we should probably look into.
Julio.
I have a question for João. Thanks for the nice talk, by the way. I'm wondering if you have any thoughts on how the MF plume framework can be, coaxed into producing realistic diurnal cycles over land, and I assume that would, if that was successfully done, it would have an impact on, the time evolution of convection over ocean. Might help our MJO and things like that. So it's a free-form question. I apologize.
No, it's a great question. Thanks, Julio. So Kai, in his 2019 paper, I think the second one, I don't know, one came first, the second one, he does show that you can use a single column model with EDMF, so basically eddy diffusivity with TKE for the smaller scale turbulence, so to speak, and then multiple plumes for the shallow and deep convection. And it does seem to be able to reproduce this nice LBA case in which you have transition from stable boundary layer, dry convection, shallow convection, and deep convection in a relatively realistic manner. Now, there's additional things that parameterization has that we don't have in there. So downdrafts and a simplified form of trying to reproduce cold pools and the sort of the enhancement of convection from cold pools and the impact on entrainment and additional surface fluxes. So those things do matter, and he also shows that. But I think it's promising, right? And the results that Rachel has also produced are sort of promising in that sense. I think that the multiple plumes have in themselves the ability to do that. The question is, how do they perform when embedded in a big complex model like CAM and having club as its partner rather than TKE eddy diffusivity? I don't know, Adam may have thoughts as well.
Well, I'll just underline one point you just said. We have pretty simple plumes. They're just updrafts, an ensemble of updrafts. The microphysics is very simple. And with that, we can simulate a host of cloud regimes, provided you're smart about how you parameterize entrainment. And so entrainment seems to be 75% of the ball game. With respect to the diurnal cycle, Julio, as you know, we're trying to figure out what is the recipe for success to get delayed onset of precipitation over the continents. And And so I don't have anything more to add as we learn about what we need to do to ensure that it's looking realistic.
Yeah, I mean, I want to add that I'm not so much talking about, you know, the well-known problems every model has over the Midwest in summer. I'm talking about just delaying kind of your standard, you know, your standard convection in warm regimes by a few hours.
Yeah, that's where the LBA case is very good at, right? That it really, and the papers from Wojciech and I think Francois Guichard show that often models have difficulties in getting timing right, and what we have shown in these papers is that it is possible to do it in single column model really, you know, fairly well with multiple plumes coupled to ED. I'm very optimistic that the same will be done with Club plus MF. And I think Adam said, you know, the key aspect of this entire story in a way is to get the entrainment right. So that's our struggle. It has been for a few months, is how do we get a formulation for entrainment that is, you know, realistic based on the physics that we can understand and are able to reproduce at the same time as sort of universal enough to allow us to do stratocumulus, shallow convection, deep convection, dry boundary layer. And it is a challenge. But it is the case that it's the lateral entrainment that really sort of controls things to a large extent. I mean, this is not too dissimilar from Eddy diffusivity parameterizations, in which it is the mixing length that actually in the end controls a lot of stuff. I mean, even in the sort of the Mallory Yamada paper from the Reviews of Geophysics, I think of 1982, that has, I don't know, 2,000 citations or something or more. At some stage, like in the middle of the paper, they will say, well, in spite of all this that we've done, and it's great, if you don't get the mixing length right, then you don't have much hope of getting things right. So turns out that the entrainment plays a similar role to the mixing length, and they are physically connected in a way, right? They're sort of length scales or inverse length scales in one case, that basically, you know, you need to get these length scales well represented in a way that is independent of the entire scheme that you have. And I think the club presentations for the momentum flux, for, you know, the two before, also say something about this and the role that certain physical entities like mixing lengths or time scales or entrainment play in getting everything, helping everything get combined in a sort of optimal way. But yeah, the entrainment is critical, and Adam is absolutely right.
And did you deactivate the Zengberg-Fallen scheme for these runs?
Yes. Yep.
Yeah.
Yeah. We did them with them on as well.
Mm-hmm.
And I think it's important to recognize that the stratocumulus to cumulus transition in CAM6 does, the cumulus part is handled to some extent by the ZM scheme. So it's not not active in the trade cumulus regions. It's doing things. And I guess I wanted to make another point about, I'm not sure if Rich is on the call, but my understanding is when ZM scheme went from using a undilute plume calculation, CAPE calculation, to a dilute CAPE calculation, that sort of helped facilitate a more realistic diurnal cycle by tying this CAPE to sort of the environmental moisture. So if there's more moisture in the environment, your entraining CAPE values are going to end up being a bit larger because you're not mixing dry air, you're mixing moist air, and that including that itself sort of creates a delay from phase lock to the diurnal cycle. And Rich is saying yes in the chat. So that suggests that the role of moisture and some information about the role of moisture might be important for getting the diurnal cycle right.
Yeah, Rich.
Yeah, I mean, one of the key things is organization with respect to moisture. I mean, early on, the convection is very unorganized and the effective entrainment rate is very low. But later on, in the presence, of a more humid, deeply humid atmosphere and raining, precipitating, then the effective organization is much lower. Sorry, higher for the early part of the day. So I'm wondering, there was this piece to Club MF that had some length scale that has some temporal evolution, and I'm wondering whether that kind of holds the key for a good, better diurnal cycle. Maybe a question for Joao, I guess.
So you may be talking about the way in which the cold pool effect is parameterized, evaporation and precipitation, and there's indeed, but those studies were essentially done in single column model, right? As far as I know, Adam has not implemented any of this in the 3D model. Correct, Adam? None of this is there, right?
The specific aggregation parameterization is not in there. That would require downdrafts, which we have not yet implemented. That said, I have 7 different nameless options for different ways to dynamically compute L that we're experimenting with, and that list keeps on growing. And so I didn't provide you any exact equations in my talk because we're still sort of figuring out what is the smartest way to inform this L value over time and space. But I did make it clear that this additional consideration of, is club producing a lot of a turbulent environment, that feedback onto the entrainment rate and the MF plumes should be considered separately than a dynamical L. But it's looking very promising in partitioning what club does well and what MF does well. And so I wanted to include that result in my talk.
But going back to Rich's question very quickly, yes. So there is a parameter and a simple, very simple attempt to parameterize those sort of mesoscale effects, and indeed there's sort of an integration in time that takes place there in representing that. But again, that's only in the single column model that is sort of independent even from SCAM. So we have not attempted that in the context of CAM.
Yeah, I mean, the issue is, correct me if I'm wrong, is that these entrainment rates are based off of the assumption there's an environmental ambient humidity you're entraining all the time. And there is, later in time during the day, there is, localized humidity, localized cloud, such that any plumes that, penetrate that particular region, which they would, because that's organization, has an effectively lower entrainment rate. And that's where I think you can get the control on the entrainment rate that might extend the down cycle peak later.
Yeah, I mean, you touch on something which is a real interesting sort of challenge for this idea of multiple plumes, and I think we haven't tackled that in a very thorough manner at all, which is, how much these plumes have to interact with each other, so to speak. And it's quite the case that you can make that when you have more complex organization, those plumes need to interact with each other, right? But that creates a completely different algorithmic animal in a way, because while for shallow convection and for convection that is still not very organized, let's use organized for lack of a better term, you can launch all these different plumes, right? And they're scattered across the grid box, and they just transport, mean properties from the subplot layer and to layers above and so on. But you don't need to know where they are, right? So that's why these algorithms are so cheap. You can use multiple plumes that reproduce a lot of the vertical mixing that exists, but because they don't talk to each other, the plumes, they don't need to know where they are. And you don't need to know where they are in the domain. And that, if you look at an LES of shallow convection from above, that's exactly what you see, scattered popcorn clouds. When you try to actually make them communicate with each other, then you have a completely different problem, right? That we're trying to start to tackle from the most simple way possible and see how far we need to go to reproduce what's actually happening. But it may well be that we will need to, at some stage, these plumes need to communicate in some form, and they need to know more or less where they are, so to speak. Exactly what that means exactly, I don't know, because I don't think we have thought about it as we've thought about it, we've done stuff, but we haven't thought about it in a way that is sufficiently thorough that we know exactly what we're going to do. But yeah, that's a fundamental problem.
Yeah,
and
I think
we work on that. But anyway, sorry, I talked too much. Apologize.
No, I think we're diving pretty deep now, and we are cutting into our break time.
Yes.
So we keep this channel open if you want to continue the conversation. Rich, others, Adam, Joe, please go on. We are now closing the official discussion, and we come back here in 55 minutes, I would say. So 12:45 Mountain Time. And we continue with the second session on physics.
So Julio, if you or Elizabeth can stop sharing, I want to test that I can actually share my screen so I don't have one of these like Mac problems.
Sure. I'm not sharing.
Oh, is Elizabeth sharing?
It must be Elizabeth because I'm not.
Okay, maybe she's not back yet. But we should have the presenter. I don't know if you've had this problem before, but it might be useful to make sure the presenters can test that they can actually share it.
Yeah, I didn't have any problems this morning.
Okay, then we'll wing it.
Well,
okay, there we go.
Looks like everybody's back.
Yeah.
I'm here, all set now. That's just a placeholder while we're on break for anybody who comes over to Zoom so they know what's going on.
Yeah.
Okay, so you can see my screen. You can see my screen now, right?
Yes.
Okay. Fine. I just want to make sure I didn't have one of those Mac things where I have to get off the call and restart Zoom before I can share my screen again. Some update thing. The usual.
All right.
Andrew, if you just give me a 2-second warning so then I can just start the recording again.
Yeah, I think Meg is actually the first.
Yeah, Meg's first.
Oh, sorry. Sorry, Meg. Just let me know when you're ready.
Julio, are you going to kick off this next session or?
Yeah, I'll just say a sentence or two and then we'll just dive right in. We're kind of on a tight schedule.
Yeah.
It's not a lot of time, unfortunately. Yeah, it's almost 12:45. So, Elizabeth, I'll be monitoring the chat, I guess, to see if there are comments, etc. Okay, why don't we go ahead and get started? It's almost 12:45. We're having another session on physics developments for CAM. We're going to be talking, going a little further afield in boundary layer turbulence, but we will. Our first talk will actually address boundary layer turbulence as well. Let me introduce Meg Fowler, who's going to be talking about atmospheric responses to land surface heterogeneity. So you want to go ahead and get started, Meg?
Sure.
All right.
Okay, can you see the screen okay?
Yes.
Excellent. Awesome. Thank you, Julio. Yeah, so my name is Meg Fowler. I'm a project scientist here at NCAR, and I'm excited to share some updates looking at how the atmosphere responds to subgrid scale land surface heterogeneity. So this is work I've been doing with a number of collaborators, both here at NCAR and at other institutions. And I'd also like to thank our funding agencies for supporting this work. So when we think about the ways that the land and the atmosphere interact in the real world, it can be pretty complex. So having even small scale differences in what kind of land surface type is present can lead to preferential formation of boundary layer cumulus clouds over some kinds of surfaces. You can start seeing mesoscale circulation setting up between, say, warm and cool patches. And at even broader scales, we see impacts in terms of liquid water path and turbulent kinetic energy. So in the real world, we have kind of a complex picture here where different land surface types are interacting with the atmosphere and with each other. But in the context of global climate modeling today, that's really not what we have. What we see instead is that despite having information on subgrid surface heterogeneity here, all we're communicating between the surface and the atmosphere are grid cell means. So there's a couple efforts that are really aimed at moving us from the picture on the left to the picture on the right. And so we're part of a climate process team called CLASP, which stands for the Coupling of Land and Atmospheric Subgrid Parameterizations. It's really driving a lot of this work forward, but it's also sort of in the broader context of developing CAM7. What we want to do is improve the ways that the atmospheric model is coupled to and interacts with the surface models, and hopefully get a better feel for how there's physical interactions and feedbacks in the fully coupled system. So we're at kind of an exciting point here where we have an opportunity to move beyond those grid cell means. So both CAM and CLM, which are the atmospheric and land model components of CESM, represent subgrid heterogeneity in their own ways. So in CAM6, as we've heard a lot about today, this is through CLUB, which is its boundary layer and turbulence parameterization scheme. the way that CLUB works is it basically predicts higher order moments of temperature, moisture, and vertical velocity by assuming a double Gaussian that represents the distribution of those three variables within a given grid cell. What I want to highlight is that it does this on a staggered grid. So at the ZM levels, which includes the surface, these are where even ordered moments are computed, so variances and covariances. So if we want to provide boundary conditions to CLUB at the surface here, what we really need are those variances and covariance of, say, temperature and humidity. The good news is that we have that within the land model CESM-5. So within a given grid cell, the way that subgrid scale heterogeneity is represented is by a series of different surface patches. So you can have various types of vegetation, say trees versus grasses. You can have irrigated and unirrigated croplands, lakes, urban areas, et cetera. And each of those different surface types has its own temperature and humidity. So ideally, what we can do then is come up with a way to link these two subgrid representations together and provide a boundary condition for CLUB. There was a method proposed to do this a few years ago in 2018 by Bocholtz and Mironov. And just briefly, the idea here is that if you have a grid cell that has two very different surface types, say we have an urban area and a lake, their temperature would be dramatically different. But what we've been passing up to the atmosphere is just a grid cell mean flux in green. What's proposed then is we can start increasing the complexity of this and pass up, say, added to the grid cell mean, how different is each tile's temperature humidity from that grid cell mean? And what we were doing is adapting this to sort of CLUB's surface variances and covariance estimates. So these are the equations set forth by Andre et al. In 1979 for the moisture variance, your temperature variance, and the covariance on the bottom. And I'll refer to this as the homogeneous calculation of surface moments. And by that, I mean that basically we're assuming that the surface is, for all intents and purposes, a single homogeneous type because we're relying only on grid cell means. So we have your surface fluxes, your friction velocity, and then a Monod-Bukov stability parameter. What we can do, again, is add on a term to represent heterogeneity. So following that Bocholtz and Mironov approach, the heterogeneous version for each of these equations would be to keep sort of your grid cell mean estimate, the homogeneous case, and then add on a term that represents the difference between each patch's humidity or temperature from the grid cell mean, denoted here as an overbar. And then the covariance would be the product of those two differences. So as it stands right now, we've enabled this in a new module within CLM, the land model. So ultimately, you have all this subgrid information. You can compute those surface moments and pass those up to CAM and CLUB as a boundary condition. So how do we actually test what effect this is having on the atmosphere? So we've been doing this in a series of single column SCAM simulations. These are forced with the Lasso-Varinel dataset from the ARM Southern Great Plains site. So 2015 to 2018, we're running this for about 3 months, June, July, and August. And then we're looking at the homogeneous and heterogeneous cases for each of those years. But I'd like to take just a second and sort of note what I mean here by freely evolve, because this has come up recently. So the way that we had been forcing SCAM had been supply the large scale forcing that you need to run the model. So the temperature and humidity, divergence, convergence, use the observed winds, but then we didn't apply any additional constraints on that. We wanted the atmospheric temperature to kind of evolve freely in response to that surface forcing of heterogeneity. But the question comes up, how much internal variability is there in this kind of system compared to that signal of heterogeneity? So one way to kind of investigate this further is to apply just really small scale temperature perturbations to the initial temperature conditions. So on the order of 10 to the negative 14th Kelvin. Compared to our original homogeneous case, applying a PERT lim of 0 gives you exactly no difference. So that's excellent. Nothing's changed. But if we start applying different values for PERT lim, here PERT 01 would be applying a perturbation of 1 times 10 to the negative 14th, 2 would be 2 times 10 to the negative 14th, and so on. Over just a 3-month simulation, we wind up getting differences on the order of 20 degrees in this case, negative 15 degrees in a different case. And so we're seeing really large drifts in very different directions and really large scale. And if we take the two most extreme cases here, that PERT lim equal to 1 versus 3 times 10 to the negative 14th, wind up getting really different surface temperatures. So this is your 2-meter temperature. Compared to observations in black from that Varinel data set, we do have a warm bias that said, we're getting up to like 135 degrees Fahrenheit at the surface here. So it is summer in the Midwest, but that's still a little excessive. The good news is that adding in any form of constraint on atmospheric temperature really does help the situation. So whether you tell the model to use the observed surface fluxes in green, the observed ground temperature in purple, or relax temperatures back to observations in teal, you bring those estimates of what's going on much closer to reality in terms of near surface temperature. And there's not as much of a difference between each of these cases, which is nice to see. So what we've opted to do is relax temperatures back to observations, but we still want to have the boundary layer really able to evolve in response to heterogeneity. So what we're doing is basically we're relaxing the temperature profile from the top of the atmosphere down to about 850 hectopascals, and at that lowest level at a really long time scale, so about 25 days, which was the teal line that you saw before. So even a light touch in terms of controlling these simulations does quite a bit. But back to our original purpose here, does heterogeneity at the surface actually impact the atmosphere in the way that we've implemented it here? One of the ways that we can look at this is through looking at boundary layer depth. So CLUB is in particular a boundary layer relevant parameterization. And if we look at the difference in afternoon mean boundary layer heights, which is the time series plotted here between the heterogeneous and the homogeneous case, what's reassuring is that some days respond quite strongly to this addition of heterogeneity. But there's really unique cases. So here we're going to look at the top and bottom 10% of boundary layer height changes. So when heterogeneity drives large increases in depth versus driving large decreases in depth. To kind of illustrate this a bit more, if we look at the average diurnal cycle over those categories. So here we have 35 days where you have a large positive delta, 35 days with large negative delta, and then averaging the other 80% of days together. Most days adding heterogeneity might not have a huge impact, but on some days it can be really pronounced. And we see that throughout the course of the day, from mid-morning down to the evening, there's a significant trend of heterogeneity to either increase or decrease those boundary layer depths. Going along with that, we see other near surface changes, which are in the direction we would expect. So sensible heat fluxes tend to increase when boundary layer heights are getting deeper as compared to decreasing here. We also see that turbulence changes. So this is another one of CLUB's higher order moments, W prime squared, which is your vertical velocity variance at the lowest level that we're looking at. And here we can see that we're increasing the amount of turbulence versus decreasing it depending on the direction of the boundary layer height changes. So more energy, more mixing, deeper boundary layer heights. But that doesn't really answer the question of what drives that differing response. So we've altered 3 surface moments in particular, and yet we're seeing these huge differences in boundary layer height. So what is the connection? To answer that a bit more, I'm going to switch from looking over time, the course of the day, to looking vertically. So these are 12 to 6 p.m. Means, vertical profiles of the temperature variance on top, moisture variance in the middle, and their covariance on the bottom. And again, we have the heterogeneous case in red. So if we look at the surface here across the top 2 columns, what you'll notice is that the heterogeneous case tends to increase those surface moments across the board. And that's good. That's in line with the equations that I showed you before, because we're adding on a term to the homogeneous case that represents how much each patch's temperature or humidity varies. And with the covariance, we actually see that we tend to go negative at the surface. That's because on average, the anomaly in temperature and moisture would be opposite sign. So you have drier patches that are also warmer, so physically expected. But what's really interesting here is to look vertically across these 2 categories of days. So when we have boundary layer heights that are increasing with the addition of heterogeneity, the anomalies in your variance are positive pretty much throughout the depth of the boundary layer up to about 800 hectopascals. On days where we have large decreases in boundary layer height, that is not necessarily the case. So here at the surface, we have an increase in these moments, but aloft, the signal of heterogeneity is actually to decrease those variances relative to the homogeneous case. What's kind of neat to see is the way that those vertical changes sort of impact other moments as well. So here we're looking at the turbulent heat flux, W prime theta L prime in CLUB. And again, we start to see that when we add in heterogeneity on days where it can act to increase boundary layer depths, we're increasing that turbulent heat flux as opposed to decreasing it. And if we start to break down exactly how these things are linked together, we can use kind of a budget analysis to understand this. I'm not going to walk through all of the terms in the turbulent heat flux equation, but I do want to highlight these 2. You have the buoyancy production term and then the pressure terms, which are trying to help balance out that production of buoyancy. This is theta L prime, theta V prime, but in a lot of ways, we can kind of approximate that as theta L prime squared. And we just saw that the vertical signal theta L prime squared is quite different on these two particular categories of days. And unsurprisingly then, if we look at the difference per term between heterogeneous and homogeneous cases, on days we have large increases in boundary layer depths versus decreases, the two biggest changes are in the buoyancy production term in teal and the pressure term in blue. So it's really that change in temperature variance that seems to be driving this right now. This also cascades into other moments. I don't want to, again, go through all of this, but just to highlight the budget for vertical velocity variance or turbulence near the surface is related in large part to that W prime theta prime term. And so as we're increasing our turbulent heat flux, we're increasing our turbulence as well, which makes sense, and it goes along with the way that boundary layer heights are changing. So there's some pretty interesting vertically complex differences in our covariances and variance that we're looking at. I will say there's also a potential role of environmental conditions in all of this. Maybe some days are predisposed to be especially sensitive to heterogeneity, though I think that's still something to explore further. But I'll also just note that, what we're looking at here is really a minimum estimate of how heterogeneity can impact the atmosphere. If you've ever been in the Midwest US, I'm sure this is not surprising to you. It's not a very heterogeneous location. It is mostly crops and grassland, and there isn't a huge amount of temperature and humidity difference over those kinds of surfaces. So what we're looking at is extending this to other locations and also including a hill slope hydrology model that's being built by Sean Swenson. We can also further improve the parameterization by comparing with against things like LES experiments to get a feel for where we can improve, including some representation of secondary circulations and things like that. So I think I can go ahead and close there, but I thank you so much for your time, and I'm happy to chat more about this. Thanks.
Thanks, Meg. I think we have time for a question. Well, I'll ask something. In your representation of heterogeneity, the atmosphere above is assumed to mix instantly, right? There's no blending height associated with your surface heterogeneity, right? It's just a single grid mean.
Yeah, we're not including any kind of blending. We're only modifying that surface moment, and it's instantaneous. Yeah.
Okay, so all the surface prognostic surface model acts based on one atmospheric value of everything.
Right.
Okay.
Correct. Yeah. Thanks.
Thanks. It's 1 o'clock, so why don't we move on to the talk on pumas from Andrew Gettleman. You all heard a little bit about pumas in the morning, and Andrew's going to take it away. Thanks.
Okay, hopefully you can see that. We got a bunch of windows out of here. Okay. All right. Get a pointer. There's my pointer.
I see your cursor moving around.
All right, I'll just use the cursor. That's fine. Thanks, Julio. So today I'm going to talk to you about PUMAs, which is sort of the next generation microphysics for CESM. It stands for Parameterization of Unified Microphysics Across Scales. And this is work that's had a whole host of people contribute to it, in addition to myself and Hugh Morrison. Trude Eidehammer's done a bunch of work on this. Zach McGraw in Oslo's put in some very useful help. Kate Thayer-Calder's done a lot of the software engineering, a lot of discussions with Richard Forbes and ECMWF. John Dennis and Jian Sun have contributed quite a bit from Sizzle, as you'll see, and then also Cecile and Jiangxu in CGD as well. So there's a whole host of people involved in this, and that sort of motivates things. The basic conclusion of this talk is, what is PUMAs? It's MG3+. It's sort of the next version of the Morrison-Gettleman microphysics. And as you can see from that first slide, it's not just you and I anymore. There's a lot of people contributing to this. And we thought in sort of making it more modular and making it more general, it's appropriate to actually change the name and kind of reflect that. So parameterization for unified microphysics across scales, that also speaks to its ambition. What we're doing now is we're documenting the changes and corrections to the CESM2 microphysical scheme and we're introducing a new nomenclature for the scheme. This is in a paper that is in development. Hopefully we'll get it submitted in the next couple of months. Some major changes are that PUMAs now comes in as an external into CAM. It has its own repository, and in that repository we have tags for different CAM versions that are brought in. PUMAs, also the name is micro PUMAs now. It's not MG anymore for the actual code. PUMAs is available with a CAM dev physics option. If you don't give it CAM dev, you get MG2 or MG3. And in this talk, I'm going to talk about the impact of the changes on mean state climate after describing them, and then briefly show some stuff on some cloud feedback response to warming and the aerosol forcing. So we've just brought this into CAM dev, and I'll target what the results are for that and sort of the development pathway. So the features for this and things that are options, MG2 and MG3 differ basically only in the availability of Grapple. It's MG3 MG2 was sort of deprecated, but you can turn on Grapple or Hail. So we're still maintaining that, but we're leaving Grapple off because at climate resolutions of 25 to 100 kilometers is not really needed, but it will matter for resolutions below that. So we would recommend that you run with Grapple below resolutions of finer resolutions about 25 kilometers or so. There's a bunch of switches. We've done some work to replicate processes in the IFS. We've been doing some testing in the ECMWF model. Those are all off because obviously we're not trying to reproduce the ECMWF IFS model. There's now open ACC directives for GPU accelerators in the code, which I'll show some interesting results on. There is a fall speed correction for rain, snow, and Grapple. The big one that most people have heard about is there's an ice nucleation fixed. We have changed the ice number limiter, which got messed up in CESM-2 by not accounting for all the ice nucleation. That's now changed to account for all the ice nucleation, and we put a limiter more structured the way that mesoscale schemes do it, just at the end of the scheme. That's a fairly high value. Won't kick in except if you start getting convective motions. We've added in vapor deposition on the snow as a process. It doesn't really do much, but it's there for consistency. And we're recommending an implicit fall speed calculation for sedimentation, which really improves the consistency of rain formation at longer time steps. And there's an option which we've turned on for accretion to see the newly auto-converted rain. This is liquid only. It's a nameless option. It doesn't have much impact as expected, but it was designed to see if we could actually change the aerosol cloud interactions that way. This is actually kind of interesting. So thanks to some hard work from the group in CISL, we've gotten basically ACC directives put throughout the code, and we've actually refactored a bunch of the loops in the code in order to do this. So we have now some experience in taking a fairly complex CAM scheme and putting that through the ringer, so to speak. What you see here is the column on the right in each of these in colors is the GPU version. The CPU version is in yellow on Cheyenne, and then Casper in blue, which has a couple of some faster CPUs. This is a kernel test, but what you can see is as you get to more work per essentially node or core, and you load up the number of columns, the GPU actually gets very efficient. It gets much more efficient than the CPU. You'll also notice that copying data, which is the green and the orangish red, copying data is most of the time, not the computation time, once you get the data loaded on the GPU. This is actually maximum correctness. It's not even optimized yet. And the implication is that if we were to put more of the physics on the GPU, we wouldn't have to do that copy every time. We would get a bigger speed up if we put more of the physics on the GPUs. We're already getting a factor of 3 as we load this up. That should increase because the computation time is much, much smaller. So that's just a motivation slide. We should start thinking about this for the rest of the physics. Sedimentation changes, we put in the implicit fall speed and continuously falling precipitation. That's in the gold colors across a range of time steps, and which you can see, particularly for ice, which falls slowly, and a little bit for rain, and snow, we're actually, with the exception of the longest time steps, we're seeing much better time step stability for the implicit calculations. These NI max changes, there was this artificial limiter on ice number in CESM-2. This was introduced when the Myers ice nucleation was removed and the Hosa et al. Ice nucleation was added, but it wasn't added to the ice number limiter. That results in more supercooled liquid, particularly in colder climates, and was not intended. And it happened when there was a refactoring of micro P aero. This was noted by Zach McGraw at Oslo. So thanks Zachary and Trude Stolermo for this. And it was picked up by Zhang Zhu, who's talked about it extensively to reduce the paleoclimate sensitivity, among other things. So that's part of the Pumas code now. That also means Pumas code is not, we haven't made that backward compatible in CAM. So it's a change that you can't undo when you go into CAM dev. So a couple of global tests. These are 8-year climatological runs and present day control, PI 1850 aerosols to look at the forcing, and SST plus 4K to look at fast feedbacks and climate sensitivity. We've done it with the control, the Pumas update, and the red is the Pumas update plus the implicit ball speed. That's the closest to the CAM dev version. The accretion changes in that red line, but you can't really see any differences in that. So one thing to note is this is the ice fraction of the control in the upper left. And if you look at the lower right, we're increasing the ice fraction throughout most of the atmosphere in what would essentially be the mixed phase region at high latitudes and at higher altitudes. And this increase in ice actually contributes significantly to the change in climate or change in sensitivity of climate, I would say. It also contributes to the change in climate. The liquid actually, the ice actually lasts. It has different reflective properties. And what we see is these are some climatological plots, zonal means. All the Pumas ones are in the colors, the control is in the black, the purple is series data where it's available. You can see we get lower liquid water path. Now this is everything else unchanged. We haven't made any attempt to tune it purposefully because we're just trying to look at what the impact is. This is intended to get combined with other CAM physics. So obviously other things are going to be changing. It reduces the liquid and ice water path. Obviously, it doesn't do anything to the aerosols. We haven't changed the aerosol emissions. It really doesn't change the cloud fraction. It does reduce the cloud drop number, doesn't change precipitation, but that actually does modify the shortwave and longwave cloud forcing. You can see the cloud long wave's down a little bit, and the shortwave is also slightly reduced here. So that's interesting in the climatology. It's obviously something we're going to have to retune, likely. What's interesting also is that because we have more ice relative to liquid, we're changing the cloud feedbacks. So if you look on the right, the adjusted cloud feedback, what you see is that the black line, or so the green line now is the control, sorry about that. That one sort of stands out here. And that's actually higher, meaning a higher cloud feedback than all these other Pumas cases. So we've actually, particularly at higher latitudes, both in the northern and southern hemisphere, we've actually reduced the cloud feedback. It's gone negative, which means more negative, which means having more ice, we have more of a negative ice phase feedback. And you can see a lot of this comes from the shortwave, which is on the left panel here. And you can see the value. So if you just look at the cloud feedback here and the shortwave, the net cloud feedback, the control is 0.7 watts per meter squared per degree Kelvin. With the implicit, we're going down to 0.54 watts per meter squared per degree Kelvin. That's actually fairly significant, 0.16, particularly when you think of a high climate sensitivity, starts lowering it fairly significantly. I'd have to look at the numbers. It's probably about half a Kelvin at least in doing that. This is just the aerosol forcing. So again, same simulations. And if you look on the far left, what happens is between the control and the Pumas implicit, we get a much less change in liquid water path. It's about half. And that actually reduces our top of the atmosphere flux from minus 1.6 net to minus 1.3. So that's a 20% reduction. The other interesting thing, which I think is actually physical, is that we had a very high long wave cloud radiative effect in the control. This is this column, the third column from the right. That's now significantly reduced. So that offsets the shortwave being reduced, but I think it's a lot more defensible and a lot more what we think should be happening. There's less of a long wave effect to the aerosol indirect effect. This just shows it for zonal means. And if you see, just looking at the bottom right, the change in drop number is significantly reduced throughout the northern hemisphere in all the Pumas configurations. So that's the reduction in aerosol forcing. Next steps for Pumas, more testing at high resolution. We're now looking at this at refined mesh versions at 3 kilometers. I think Bill Skamrock may, or I think Dave Randall may talk a little bit more about that tomorrow. And I'll show some examples of that, or sorry, Wednesday. We're doing analysis of Puma's part of the CAM6 perturbed parameter ensemble. Trude Eidahammer is going to talk about that. And that's going to help us do some analysis. I've got to look at that for tuning purposes. One other thing we may want to put into the next version into CamDev is we've refactored the auto conversion and accretion. We're emulating a stochastic collection kernel. And this might be worth including for CAM7. It really improves the high frequency performance of what the rain formation looks like. Doesn't seem to have much of an impact in our preliminary tests on aerosol indirect effects, interestingly enough. But that's actually been published in a paper. We have one more iteration to do with that. That's actually using a machine learning neural network to do the emulator in there. But I think it's pretty robust if we get the second version done in the next couple of months. And we have support through the LEAP ST Science and Technology Center to do that with Columbia. And that's with DJ Gagne and Jack Shen. Two other farther out developments. We have a P3-like unified ice that's been put in there by Trude Eidehammer. We are going to get back to that in the next 6 months. We haven't looked at tuning that yet, so I'm not sure that's going to be ready for the next version of CAM or CESM, but it is interesting, and we have to take a look at that. And then we're actually going to try incorporating even further a flexible framework for the structure of liquid size distributions. This comes from Hughes Boss work, and maybe even a single category liquid. I don't think those are on track for the next, baseline model for CESM. And then we are pushing forward with some software engineering. We're about to remove all the packing and unpacking, which has created lots of problems, and removing or adding CCP metadata and rewriting the CAM interface as we go into that, hopefully in the next year. So lots of updates in the microphysics. Mostly you should think about the NI max change and this implicit fall speed. This reduces the cloud feedback and the climate sensitivity. It reduces the aerosol forcing. It is going to require some retuning of cloud physics. And we're moving forward with some other, I think, really fun development activities, which are going to be valuable. And we're doing tests of this at higher resolution. I think the scheme's pretty good at working across scales. And with that, I think I'm going to stop. That's it. Any questions?
Thanks, Andrew.
There's a question from Simona, if you want me to pick that one up.
Yeah, go ahead.
So Simona's asking, how does the increase in ice and change in clouds compared to observations? Does it go in the right direction? There's not a lot of observations of this, but we have looked against the Socrates in situ comparisons, and it does go in the right direction. We tended to have too much liquid, too much supercooled liquid in most environments that we've looked at, not enough ice. And so we're increasing the ice fraction. That's probably a good thing. So the problem with getting this right, the really tricky part is if the climate sensitivity is dependent on this thing at high latitudes, it's a really tight balance because we know there is some supercooled liquid. We just don't know exactly quantitatively how much. Okay. Why the aerosol forcing is reduced. I think actually it has to do with the implicit, some of it's the implicit fall speed. Not sure exactly why the rest of it's reduced. I'll have to go back and look at my notes on that. Good question.
I have a quick question. In sort of our first light PUMA's results with CAM7, it was my impression basically that clouds got a lot thinner. Is that correct?
Yeah, that's correct with what I just showed. It's consistent with these earlier results.
So
the issue I think is that it's just the lifetime potentially of the ice is one of the issues. So that the lifetime of the ice, if you add ice, the lifetime of the liquid is less. That makes the clouds a little dimmer, and it also makes them fall out faster.
So it's not just having more ice in the clouds. It's also that they're around less.
Yeah, their cloud fraction is the same, but there's less liquid water pass, so they're thinner.
All right.
And they're dimmer. One GPU. Oh wait, Peter's asking. No, I'm not saying that. It's just that one GPU I don't think is faster than 144 CPU. I have to actually look at that number. We'll have to talk to John about that. And Zhang, no, it's not in the PPE. I can answer the rest of them in the chat if you want me to keep going.
Okay. Yeah. If you don't mind addressing some of the remaining questions in the chat, we'll go ahead and move on to the next talk from Xi Zhao.
Yes.
On Socrates. So thanks, Andrew. And why don't you please go ahead and start?
Oh, yeah. Can everyone see my screen?
Yeah.
Okay. Thanks, everyone. My name is Xi Zhao. I'm a postdoc in Dr. Xiaohong Liu's group. Today, the title of my talk is important as process processes are missing by the climate model in simulating the Southern Ocean mixed with cloud. So first, I will show you the motivation for us to do this work. This figure shows the supercooled liquid fraction at different temperature over the Southern Ocean. The supercooled liquid fraction is calculated by the liquid water path over the liquid water path plus the ice water path. We notice that climate models has very large uncertainty in simulating the cloud phase over the Southern Ocean. Particularly, the CESM-2 model and the E3SM model reported too much liquid and too less ice cloud phase bias. And this cloud phase bias further result in a less negative cloud feedback over the Southern Ocean and further result in a high climate sensitivity. We notice that the climate sensitivity in the CESM-2 model is 5.5 K, much higher than the previous model version. So we notice that there are large cloud phase bias over the Southern Ocean. One potential important reason is current cloud physical processes are parameterized based on the observation over the Northern Hemisphere. Therefore, may not well represent the aerosol and cloud processes over the Southern Ocean. For example, the ice nucleation process is parameterized based on the observed dust aerosol number concentration and observed IMP number concentration over the Northern Hemisphere. However, over the Southern Ocean, where dust aerosol has a limited amount, how the ice is formed there is unknown to us before. Luckily, recently we have more new observation data over the Southern Ocean, like the Sakoti campaign, Capricorn campaign, Marcus and Mercury. So our work is trying to bridge in the gap from the new findings in the new observation data over the Southern Ocean to the model cloud phase bias to improve the model cloud phase bias over the Southern Ocean. Particularly in the observation, we notice that the marine organic aerosol is important for the ice nucleation over the Southern Ocean, and the secondary ice production is very important for the ice formation over the Southern Ocean. So Dr. Xiaohong Liu and I, we implemented the ice nucleation of the marine organic aerosol and also the secondary ice production into the CESM-2 model. Try to improve the too much liquid and too less ice cloud phase bias over the Southern Ocean and the related cloud feedback and high climate sensitivity issues in the climate model. So the observation data we use is from the Sakoti campaign, like the CCN data, ice number data, ice water content data, and liquid water content data. The IMP observation data is from the Capricorn campaign, which is also conducted over the Southern Ocean. We use the CESM-2 model to conduct the 3 simulations. The first simulation is control, which is using the default CESM-2 model. The second simulation is called MOA, which is based on the control simulation by adding the emission, cloud droplet activation, and ice nucleation process of marine organic aerosol into the CESM-2 model. The third simulation is called SIP, which is also based on the control simulation by implementing the secondary ice production into the climate model. So this is a different flight track during the Sakoti campaign. We notice that the Sakoti is conducted over the Southern Ocean. Now I move on to our result part. Firstly, I will show the CCN effect and IMP effect of the marine organic aerosol. In the second part, I will show how the secondary ice production influences the ice number concentration in the Southern Ocean cloud. Now let's begin with the first part. This figure shows the temporal evolution of simulated and observed CCN number concentration during the cycle-T campaign. The orange is from the control simulation. The green is from the MOA simulation, while the black dots is the observed CCN number concentration. The gray solid line is the altitude of the flight track. We notice that in the control simulation, the CCN number concentration is underestimated by 1 or 2 orders of magnitude. If we considering the marine organic aerosol and its related chromatographic activation in the climate model, we notice that this underestimation is much more improved, and the simulated CCN number concentration is increased by up to 2 orders of magnitude and get a better agreement with the observation. We also notice a better temporal evolution and vertical variation of the simulated CCN number concentration in the MOA experiment. This figure shows the global change of CCN due to marine organic aerosol. This is from the 10-year simulation, try to give a climatology perspective of the influence of marine organic aerosol. We notice that the CCN is increased by 13% over the Southern Ocean. If we look at the seasonal variation, we notice that the CCN is significantly increased during the summertime over the Southern Ocean. We look at the CCN effect. Now we move on to look at the IMP effect of the marine organic aerosol. In this figure, the x-axis is the observed IMP number concentration, while the y-axis showing the model simulated IMP number concentration. If we only considering the dust aerosol at the source of the IMP concentration, we notice that the simulated dust IMP number concentration is underestimated by 1 order of magnitude compared with the observed IMP number concentration. However, this is because dust IMP has limited influence over the Southern Ocean. However, if we considering dust IMP plus the marine IMP, we notice that this underestimation is much more improved if we considering the marine organic IMP in the climate model. This is because the marine IMP is prevalent over the Southern Ocean. If we look at the relative importance between the dust IMP and the marine IMP, in this figure, this figure showing the marine IMP over the dust IMP. If the color become more red, that means the marine IMP is more important. From this figure, we notice that the marine IMP is more important than dust IMP over the Southern Ocean. So to summarize this part, we notice that the marine organic aerosol is important aerosol over the Southern Ocean. From a climatology perspective, the marine organic aerosol increased the CCN by 13% over the Southern Ocean during the summertime, and this increase can be 2 orders of magnitude during certain flight of the cycle-T campaign. We also notice that the MOA is dominant IMP particle over the high latitude Southern Ocean and particularly important for the boundary layer cloud. Now I will move on to investigate the secondary ice production influence on the cloud. So this figure shows the simulated ice number concentration from the control simulation. The x-axis is the time, the y-axis is the altitude. This figure shows the simulated ice number concentration from the SIP simulation. And this figure shows the difference between the SIP simulation and the control simulation. We notice that after the model considering secondary ice production into the model, the simulated ice number concentration is increased in the boundary layer cloud and upper level cloud. We also compare the simulated ice number concentration with the observed ice number concentration along the flat track, shown as the black line in the third figure. In this figure, the orange is simulated ice number concentration from the control simulation, and the black is from the observation. We notice that the model significantly underestimates the control simulation, underestimated the ice number concentration by 1 to 2 orders of magnitude. However, if we considering the secondary ice production into the model, which is shown as the green dots, we notice that the ice number concentration is increased by 1 to 2 orders of magnitude and get a better agreement with the observation. We also calculated the ice enhancement ratio between the control simulation and SIP simulation. The ice enhancement ratio is calculated by the ice number concentration from the SIP simulation over the control simulation. We notice that the ice enhancement ratio can be up to 4 orders of magnitude, and particularly the moderately cold cloud has a larger ice enhancement ratio. This figure shows a statistical analysis of the simulated ice number concentration compared with the observed ice number concentration at different temperature. The orange is from the control simulation, green is from the SIP simulation, black is from the observation. We notice that control simulation significantly underestimates the observed ice number concentration. If the model considering the secondary ice production, this underestimation is much more improved. And especially for the moderately cold cloud with cloud temperature warmer than -20 degrees Celsius. We also quantify the relative importance between the primary ice nucleation and secondary ice production, shown as the pie chart below at different temperature. We notice that for the moderately cold cloud with cloud temperature warmer than -20 degrees Celsius, SIP contribute 18% of the total ice production. However, for the colder cloud with the cloud temperature below -20, we notice a competition between the primary nucleation and secondary ice production. If you are really interested in those competition mechanism, you can further look at our paper, which is just accepted by the ACP.
Ji,
yeah,
we're sort of at the end of our time. If you could.
Oh yeah. Yes.
Okay. Thank you.
So my work is trying to bridge in the gap from the observation to the model. We noticed that marine organic aerosol is very important for the cloud initiation, and we also noticed that SIP is very important for the cloud evolution, and that's our conclusion. Thank you so much.
Yeah, thank you very much, Ji. Since we are a little bit over, why don't we move on to the talk from Xiaohong? And yes. I'll just mention that there was a question about what secondary ice production means, and maybe Xiaohong can address that question quickly yes. in his talk. Xiaohong, we can't hear you.
Sorry, I'm muted. Can you hear me now?
I can hear, but we can't. Yeah, there we go.
Okay. Okay, so she already gave an introduction to the secondary production. So I'm going to talk about our implementation of the secondary production in the CESM-2 and the study of the impact of secondary production on the high latitude cloud and also indirect forcing and the climate sensitivity. And firstly, I want to acknowledge Xizhao, who did most of the work, and Jiang Zhu and Yiqing and Mark Zelinka and Steve Klein, who provide assistance in diagnose the cloud feedback and the climate sensitivity. And I'd like to also encourage the funding support of DOE, ASA, and RGMA program. And the previous studies, like the Tan et al., they find a positive relationship between the supercore liquid fraction, which is defined as the liquid water pass over the total water pass, and had a good relation with the equilibrium climate sensitivity, or ECS. So with the increase of the supercore liquid fraction SLF, then the ECS increase. And we know that CESM-2 had the ECS of 5.5 Kelvin, which is higher than many of the GCMs in the IPCC. And this high climate sensitivity may indicate there's some issue with the cloud phase in the model, and like the too high supercore liquid fraction, for example, too much liquid and too less ice in the model. That may indicate there's some misrepresentation of the cloud process. For example, the secondary ice production or SIP process is missing in the model. And the observation often show that ice number can often be orders the magnitude higher than the ice nucleating particle IMP number concentration. So this figure showing the ice crystal number or ice nuclear number, ice nucleating particle number concentration as a function of temperature. You can see at the warmer temperature, warmer than -20, the ice number could a few orders magnitude higher than the IMP number, so which show it at the dashed line there. That indicating the secondary ice production are important, particularly at the warm cloud, supercore, moderate supercore cloud. And so what is the secondary ice production? And so secondary ice production is a process which produce the new ice crystal in the presence of the ice crystal, which are formed from primary ice nucleation on the IMP or ice nucleating particles. So they are the secondary process. And so far there have been 4 SIP mechanisms have been identified. One is the rime splintering and called the Hallett-Mossel process. And the second one is the ice-ice collision fragmentation and the droplet shattering during the rain freezing, and then the ice sublimation fragmentations. And so we have been implement the new SIP as a secondary ice production process into the CESM-2, and we have conducted 2 model experiment, and one is the controlled model with the default CESM-2, which has the rime splinter or Hallett-Mossel process considered, and then we add in the 2 new SIP process like the ice-ice collision fragmentation and the rain freezing fragmentation into the model. So we have two model experiment, and we the model is run with prescribed SST and at 1 degree, at approximately 1 degree horizontal resolution with 32 vertical levels. And the model simulation are 20 years, and we for each experiment we conduct present day aerosol emission, pre-industrial aerosol emission. The purpose is the two simulations to look at aerosol indirect forcing. Additionally, we also conduct pre-industrial aerosol emission, but perturb the SST by 4K. The purpose is to look at cloud feedback and climate sensitivity. And before we move on to look at the aerosol indirect forcing and the cloud and the climate sensitivity, we evaluate the model by comparing the model simulation with observations. So this is showing this figure shows the subcore liquid fraction. So that basically here 0 means pure ice cloud, and this is 1 is mean pure liquid cloud. And as a function of normalized height, this is like 0 is a cloud base and 1 is cloud top. For the single layer mixed phase cloud observed during the DOE ARM and PACE field campaign, and this showing the observation, you can see that at the upper portion of the cloud is a high subcore liquid fraction, means the liquid dominate. At the low portion of the cloud is more mixed phase, and there's more ice. And why, if you look at the controlled model simulation before the CSM2, you can see the model overestimating subcore liquid fraction are mostly pure liquid cloud. By only at the low portion of the cloud, you have see some mixed phase. So when we add in the secondary production process, you can see the model predict the subcore liquid fraction between 0 and 1, the more indicating the more mixed phase cloud compared with the control model, and agree with the observation better. And this is this table showing observed the mixed phase cloud occurrence, like the 63%, and during this MPACE single layer period, and why the control model only show 27% during this period, and why we're adding this, when we add in the SIP process, it's a increase to the 58%, agree with the observation much better. So the adding SIP process basically leads to the more mixed phase cloud. And we also compare with the Southern Ocean, for the Southern Ocean mixed phase cloud. And as she said, that is for the Southern Ocean cloud during the Socrates campaign. And this figure showing the probability, the occurrence of the cloud, different cloud phase at the function of temperature. And this is from observation. You can see with increase of temperature, you can see the ice, pure ice cloud decrease, and pure liquid cloud increase, the red, and the mixed phase cloud, is green, and it's sort of change. And why, if you look at a control model at default CSM2, it's overestimating the pure liquid. You can see particularly at high temperature, pure liquid cloud, and honestly the pure ice cloud, if you look at the blue curve. So when we add in the SIP process, we can see we decrease the pure liquid cloud occurrence, and compare with control, and we increase the pure ice cloud occurrence compared with control, and agree with the observation better. And this table also summarizes all the type of cloud observed during the Socrates. You can see the pure liquid, pure ice, and mixed phase observation. And so when we add in SIP, we increase pure liquid from decrease pure liquid cloud from 0.4 to 0.27. Agree with better with the observation, and the ice cloud increase from 0.35 to 0.5, and agree with observations. So when we add in the secondary production process, it leads to the less pure liquid cloud and more ice phase cloud. And this is showing the global impact of the adding the signalized production on the liquid water path and ice water path. This is the zonal mean. So this is the different latitude. If you look at this liquid water path and ice water path, and the gray line is from the observation, and the orange showing the controlled model, and it's you can see clearly that the model always made in the liquid water path at a high latitude. And when we add in the signal ice production, it's decreased significantly over high latitude. Agree with the observation much better. And also when we add the SIP process, it's increased ice water path compared with the control model. And we also look at the cloud feedback, and so you can see the this is showing the total cloud feedback and total shortwave cloud feedback, and this is also the latitude. You can see that if you compare this control with the SIP adding signalized production, and it's make the cloud feedback more negative or less positive in the high latitude. So when we add in the SIP, and we find out that the cloud scattering contribute the different component, and so the cloud scattering contribute the most to the change, and then we look at the effect on the signalized production on the equilibrium climate sensitivity. So we show that the cloud feedback is decreased in the from the for the control simulation to the when we add in SIP from 0.7 to 0.53, and the equilibrium climate sensitivity ECS decreased from 5.5 to 4.4 and by 1 Kelvin. So we further look at the aerosol indirect forcing, and this is the PD minus PI, basically this change of the difference between present day and pre-industrial. And let's first look at the cloud droplet number concentration change, delta CDNC, and let's latitude, and the delta is positive, means the increase of droplet number concentration because of anthropogenic emission from pre-industrial to present day. And if you look at compare the two models simulation, if you're adding SIP, the droplet number increases become less because you have less liquid or less pure liquid cloud occurrence. So basically you have less liquid for the aerosol to act on. So the aerosol, the droplet number increase become less by you adding the signalized production. And it's a liquid water path change indicating the secondary aerosol indirect effect. The liquid path is increased, but if you look adding the SIPs, the increase is reduced. And further, you can see the aerosol indirect forcing become less negative in the mid latitude northern hemisphere, and even become more positive in the Arctic regions. And this is showing the correlation of liquid water path change and aerosol indirect forcing. So basically, this is the control model. So this when we add in SIP, it shifts towards the left corner, and so basically liquid water path change and the ACI both decreased. And, so this is a summary, and this study we implement the two new SIP process in the CSM2. We found adding SIP change the cloud phase, and in particular at high latitude, so less liquid phase and more ice phase, decrease liquid path, increase ice water path. It better agree with the observations, and cloud feedback decrease, and the climate sensitivity decrease by 1 Kelvin. And correspondingly, the aerosol indirect forcing reduced from 1.7 to minus 1.56 watts per meter. Thank you.
Thank you very much, Xiaohong. We have one question that maybe you can address real quickly from Yuan Wang. Do you want to ask your question, Yuan?
Okay. Yeah. Can you hear me?
Yes.
Yeah, Xiaohong, I just want to clarify your SIP experiment. Do they account for like IMP parameterization from marine aerosols?
Yes, yes, we include every MOA IMP. The difference only no, we don't. The difference this is the control is the default CSM tool,
Okay.
and then we add in the SIP. We don't have the marine organic.
So I would expect if you add this new IMP, that may buffer some of the SIP impact you are looking at here. Is that right?
Yeah, likely because of the over the southern hemisphere, southern ocean, that SIP. But as she already said that showed that the ice over the southern hemisphere, southern high latitude seems mostly from the at a warmer temperature, like -20, most from the signal ice production. But adding the marine organic IMP could buffer the cloud feedback.
I see. Thank you very much.
Yes.
Yeah, thank you, Xiaohong. There's an active discussion in the chat about Southern Ocean processes, and we'll have a discussion after Jack's talk. So why don't we move on for the last talk of the day on organized mesoscale convection and its impact on tropical variability. And the speaker is Jack Chen. Do you want to go ahead and share your screen and get started, Jack?
Sure. Thank you. I'll share my screen here. Okay. So first, I would like to acknowledge my collaborators, Yaga, Mitch, Shanghai, and Ankar. So basically, the goal here is to represent the unresolved mesoscale convection in GCMs due to the inadequate horizontal resolution. And here's a little diagram taken from Munkert et al. 2017. So the goal here is just to represent this mesoscale convection, featuring this mesoscale downdraft and the trailing overturning ascent region. You have this heating profile, pretty simple parameterization. So basically you add cooling tendency in the lower portion of the troposphere and heating tendency in the upper portion of the troposphere. It's simple sinusoidal wave. And here we argue that you tend to see mesoscale convection occurring when there's vertical wind shear. And the formula actually here ties the mesoscale heating tendency to the deep convection, and with a tuning parameter alpha 1. And to determine what alpha 1 should be, we conducted high horizontal resolution warp simulations, and we picked up like 2 scenarios where deep convection happens. And the red curve here is actually where we find reflectivity being very, very high. That's where deep convection happens, and they sum up the heating tendency of over those grid points. That's the red curve. And in the surrounding grid points, where the reflectivity goes above a criteria, we determine that's mesoscale convection. That's the blue. The combined effect is the black. And they show pretty similar results in both scenarios. And with these results, we determined alpha 1, that tuning parameter, should be between 0.3 to 0.5. And for the wind shear I mentioned earlier, we tried 3 different values in our simulation: 3, 5, 7.5. That's the wind zonal wind difference between surface and 600 hectopascal. And then I will show you results from CAM or CESM and E3SM results. Before I get into the results, I'll show you the impact of this parameterization. And the left panel is the impact of the mesoscale heating rate. This is averaged out within a month. And so there's no surprise you get cooling in the lower half of the troposphere and heating in the upper portion. And the red curve represents alpha being 0.3. When alpha is 0.5, you get bigger impact. However, on the right, this is the total heating tendency combining the deep convection. So you can see the total impact. Here you see the black being the control, the baseline model. And for the red and the black, they show, okay, in the lower troposphere, and there's no surprise, the heating gets a bit lower because you add cooling. But even at about 600 hectopascal, you see the blue being quite a bit lower than the black. That's counterintuitive because you add heating here. So the reason being, when you implement this heating cooling tendency, whenever convection is triggered, you further stabilize this troposphere. So the occurrence of deep convection gets less frequent when you introduce this parameterization, which has a lot of ramification on the simulation. I'll emphasize now. So here I go through the tropical variability change due to this parameterization. First, the atmosphere component of E3SM or EAM. So this is the Wheeler-Toledo's diagram. You look at Kelvin waves. So this is ops from trim, and this is the baseline EAM. You can see the baseline model shows quite a bit weaker Kelvin waves from ops. When we introduce this mesoscale convection heating, it seems to help us Kelvin waves a bit, especially when we get to 0.5 for the tuning parameter. And the lower panels are when we introduce a wind shear trigger at 3, 5, and 7.5. As you will expect, when you set the wind shear trigger being higher, this mesoscale convection heating cooling parameterization will be triggered less frequently. So you will expect a smaller impact. That's what's shown here. And for Chem 6, it's showing fairly similar results. When you introduce this mesoscale heating, it enhances Kelvin waves. This is the MJO spectra, OLR. So I shift gear here. I jump into the couple simulation. The upper panels are from the E3SM. So baseline model showing something. So we want to focus on the spectra between 30 and 90 days, and it should be east propagating. And it's shown, the upper panel shows that when we introduce mesoscale heating, we get more power within this window. When we set alpha 1 equals 0.5 without a wind shear trigger, it seems to overshoot quite a bit. But when we introduce a wind shear trigger, it tones down this spectra a little bit, and the lower panels are from CESM-2, showing fairly similar results. So it adds power to the MJO here. So introduce mesoscale heating. And here's the MJO-like composite plot. So again, the top panels are from E3SM. The lower panel are from CSM. So I'll talk about first the baseline model. They seem to show the same kind of feature here. So once the convection enters the maritime continent, it seems to just die. It doesn't continue the propagation of the baseline model in both scenarios. But when you introduce this mesoscale convection parameterization, the propagation continues. It is capable of propagating through the maritime continent. I'll point out, as I prepare for this talk, I found out something. I think I don't have the ops here, but I'll show you later. For ops, comparing with ops, say for the alpha equals 0.5, the convection getting into the tropical West Pacific is probably a bit too strong, leading to this in phase one, it's still showing pretty strong convection in the tropical West Pacific, which is not found in ops. And the reason being, here's the precipitation biases. The first panel in both rows are from, this is biases against ops. So I'll point out in both models, by the way, this is DJF, precipitation biases. For both baseline models, it produces very strong positive precipitation biases in the maritime continent. That seems to indicate convection is too active in this region, and that's why when the convection, the MJO propagates through this region, it has trouble getting through because the convection simply is too active, taking off most of the low-level moisture. So it prevents the MJO to propagate through this region. And the three panels on the right are from MCSVs. Alpha equals 0.3, 0.5, and 0.5 with a wind shear trigger at 3 meters per second. And they all show, these 6 panels are against the baseline model. They all show a reduction of precipitation in this region. And that's the reason why the MJO can propagate through this region and shows improvement in the MJO simulation. Here, I'll quickly summarize what I have so far. We have introduced the metric scale convection parameterization, and we use the high resolution work simulation to determine that tuning parameter alpha. And we see the implementation of metric scale heating improves Kelvin waves and strengthens the MJO. And the MJO is capable of propagating through the maritime continent. And the reason being the parameterization stabilizes the troposphere, making the overly persistent convection to be less persistent. And I'll point out the last point raised when we prepare a paper on this work. John and I'll argue actually this approach is a better approach to improve the MJO than simply tuning the deep convection parameterization, because it is found when you just simply try to tune the model without representing the mesoscale convection in the model, it tends to, you can improve the MJO by tuning the parameterization, but you will sacrifice the mean state. So this mesoscale parameterization seems to be a better approach. Next, I'll shift here to the second portion of the talk. I'll get back to this chart. In addition to heating cooling tendency, there's also momentum transport associated with this mesoscale convection. So basically, the formula is again fairly similar. We add westerly tendency in the lower portion of the troposphere and easterly tendency of the troposphere, and it's go by a cosine function. And here there's a free tuning parameter, alpha 2. We follow the paper Montgomery et al. 2017 setting at 1 meters per second per day. By the way, it is harder to determine this alpha 2 using the word simulation because it's harder to determine what's the background meteorology and what's associated with deep convection and mesoscale convection. So it's hard to deduce this alpha 2 from the work simulation. So we go by this paper published in 2017. So here I show, again, Kelvin waves from this again. I didn't try this in CSM2 yet. I only tried this in E3SM. This is fully coupled model. So again, the baseline model is showing weaker Kelvin waves. And when we introduce heating, the enhancement of Kelvin waves is not as significant as in the atmosphere-only model, EAM, but still shows some improvement. And when we introduce momentum transport only, it actually weakens the Kelvin waves. That's not really something we like to see because the baseline model is already showing two Kelvin waves being too weak. But however, we combine heating and momentum transport kind of restores the Kelvin waves a little bit. And here's the MJO spectra showing both heating, mesoscale heating and momentum transport enhances MJO. So when we combine them, it's actually pretty good MJO. Finally, the MJO light composite flux. Again, if you look at the baseline model, it had trouble. The convection had trouble propagating through the maritime continent, and it's showing the same feature when you introduce momentum transport on it because it doesn't seem to do much to alter the characteristics of convection. However, when we introduce heating, the MJO seems to be just fine propagating through this region. And I'll point out this region in phase 1. This is when we introduce heating only, this is getting too strong. But when we introduce momentum transfer, it seems to correct that. So that's a nice feature to see. So finally, I summarize. So the reason why we see the Kelvin waves being weaker when we introduce momentum transport in this polarization is because we have easily in the upper troposphere, so it kind of pushes perturbation in the wrong direction. But the momentum transport component also improves the MJO like mesoscale heating. Combining heating with momentum transport seems to restore some of the Kelvin waves lost. Finally, when we combine mesoscale momentum transport with heating, it kind of reduces the strong OLR perturbation in the early phases of the MJO light composite. And that's all I have today for questions.
All right, thank you, Jack. There is a question from Rich. Do you want to go ahead and ask it?
Yeah, Jack, nice talk. Are you applying this kind of redistribution based on the shear consistently to other fields from the ZM scheme, like precipitation source region or the humidity tendencies?
I will need to think about that. That's actually something we've been thinking about because what I didn't show here is that we have trouble in JJA. The precipitation actually, the precipitation biases in JJA actually gets worse. And we've been thinking how we might formulate this wind shear trigger to help with that, because it does help with the DJF precipitation biases, but it actually makes the precipitation biases in JJA worse, far worse. So as a matter of fact, I was about to reach out to you to get help on this. Because this is not, this is something which we hope to improve over this. And one thing we were thinking is that how we can formulate this trigger in a different way so we don't screw up the JJA precipitation.
Okay, thanks.
Thank you.
All right, well, thanks to Jack and thanks to all the other speakers. We now have a discussion session. We're a little bit late, but we still have 25 minutes of discussion. I suggest that for the first 10 or 15 minutes, maybe we try to focus on the session that just happened and ask speakers from that session some follow-up questions. And then we can open it up to a general discussion. So
I guess I could start off just because it regards Jack's presentation. And Joan Alexander also had, I think, a very similar question in the chat. It seems like it's sort of an anecdote that when the ZM scheme is more or less active in these critical maritime continent West Pacific regions, that sort of facilitates eastward propagation of the MJO. Is it just an observation of model behavior, or do we understand the actual mechanisms on why that occurs? So this is a question for Jack.
I think based on what I understand from doing all the work, it seems to correct when obviously the baseline model is overly active in that region specifically, and that seems to indicate the model is missing some physics, and this added physics kind of correct that. It's actually, let me just to be sure, I recall the deep convection is also overly active in the Eastern Pacific, tropical Eastern Pacific, over like Colombia. It also corrects that when you add this parameterization. So overall, it seems to correct where convection is overly active. So it's not only the MJO, also just overall corrects where convection is overly active.
Okay. Yeah. So it sounds like there is some reason that it occurs, and it would take a lot of diving into the ZM scheme to see why, when it's overly intense, it kind of doesn't move. Yeah.
Or another way to put it is that you miss some physics in there because you don't represent it.
Okay. Yeah.
That's the goal. Yeah, that's the goal.
Tracks better with the MCS improving this. Okay, I'll stop talking.
So I had a follow-up that it's kind of on the topic of what missing physics you might be capturing with this parameterization. I was wondering in the profile you showed of heating from WRF, do you have an understanding of, for example, what process is causing the cooling in the lower atmosphere? It looked like one of the corrections you add is to cool in the boundary layer. And I'm wondering if you know whether is that for re-evaporation, for example, or what's the origin of that?
I think it's due to the evaporation. It's the cold pool to represent the cold pool of this mesoscale convection.
So you do think it's rain re-evaporation that's causing that low level cooling?
Yeah, I think so.
Okay.
I would, the Mitch Moncrief, yes, that's correct. It's the re-evaporation which is put in by the MCS perturbation in the lower levels, mostly due to the evaporation.
So could that be taken as an indication that that on top of many other things, we're not re-evaporating enough precipitation in CSM?
I think that's correct.
Right.
Yeah.
That's actually consistent with Jian and Jiang had done an experiment a couple weeks ago where he increased the ZM evaporation rate and it increased the eastward propagation of MJO. Julio, I know you saw that talk.
Yeah. Okay. Okay. So there's a question from Louisa for Meg. I'm wondering if there are any questions for the speakers in this. Oh, Meg was in this session. Sorry, of course. Yeah. Do you want to go ahead and ask it, Louisa?
Sure. I was just wondering. It seems like your work could have a big impact on the distribution of gases and aerosols in the boundary layer, and maybe even could help evaluate the impacts, looking at observations in the boundary layer. Wondered if you thought about that at all.
Yeah, that's a really interesting question. I have not given any thought to, the chemistry impacts of this. I think it would be captured, in the differences we're seeing with generating more or less turbulence, changing the surface fluxes a bit. I could see where that would definitely have a role. But no, I haven't thought about that. That's a really interesting connection. Yeah.
Well, I've been thinking about deposition some more, and so it all ties together. So maybe I'll be in touch and we can talk about it some more.
Yeah, that'd be awesome. Thank you.
Thanks.
Thank you. There's a question from Thomas to Andrew. Andrew thought he might have to leave early. I don't know are you still there? Okay. Yeah, why don't you get in touch with Andrew separately, Thomas?
We have a chance tomorrow. Thanks.
And there's a question from Joan. Do you wanna ask it, Joan?
Well, it's a topic we already left. My original question earlier was indeed very much like Adam's, but just following up, I wondered if the improvement of the precipitation biases due to or by the mesoscale convection parameterization, whether that might be related to improvements in the Walker circulation and reducing the wind biases. It's just a thought. And that was to Jack and Yaga.
Yeah, and I think Mitch probably might have an
input. Yes, Joan, I think you got something there. Sorry, I think I'm gonna just a sec. Yeah, yes, I think the momentum transport is a really important bit of the MCS parameterization, and that has a direct effect on the winds, and particularly for the up shear sloping tilt of the circulation, you introduce a eastward momentum transport, and this has has an important effect, particularly in coupled models. I think Jack showed nicely that the biggest effect was not on CAM, it was actually on the coupled simulations. So I think that this momentum transport enhanced easterly, and there are also some westerly inducement too, has a big effect on the ocean through the evaporation process and so on. So I think what you're really broadly saying is correct. There is implications for the larger scale Walker circulations through the surface and so on. Yeah.
Thanks, Mitch.
So I have a quick question. Does since this low-level cooling is due to re-evaporation, do you add water as well? Do you add water vapor in the?
No.
Okay.
No.
All right.
This is Rich again, just to keep following up on this. I mean, are you not, given the big changes in heating, at least with respect to the kind of shear that you showed, aren't you surprised that it doesn't have a huge effect? I'm kind of, in some ways, you're changing something that is, it ends up being very different in terms of, the way the waves, single-sided heating versus, double-sided. Maybe Mitch and Jack.
Yes, there's a point that hasn't come up here yet. This business about cross-scale structures. This backward tilt of the MCS also occurs in superclusters, and it also in some types of waves. And so there is this business of upscale evolution of the organization. We haven't looked enough into that in the models, but I think it's a very good thing to be looking at, because you know, this business about self-similarity across scales. You know, you introduce a very large scale perturbations on the heating and the momentum. And this is a lot to do with what I would call the finite amplitude nature of the MCS parameterization. With the MCS parameterization, you're exchanging layers of the atmosphere. You know, you're actually moving atmospheric layers up and down. And this doesn't happen necessarily with cumulus parameterization. And this has got a lot to do with this business about similar structures across scales from 10 kilometers to maybe even 10,000 kilometers. And this is implicit in this. I think there are new undiscovered scale selection principles going ahead. And I hope that in the future we take pay more attention to this, because the linearized theory of scale selection in the tropics particularly is very poorly understood. And the fact that linear side of this is not understood at all, it's not very effective even. But what we are seeing with this business about, you know, multi-scale sort of structural similarity, I think we need to look much more carefully into the nonlinear scale interaction problem. And this is something that the mathematics group is looking at rather carefully. So I think it might be in the future, you know, quantified. Thank you.
I was hoping, while it's still fresh here, to ask Xiaohong and Xi, my impression in the talks that you gave and that Andrew gave was that that some of the PUMA's modifications and your approaches to increasing ice numbers in the Southern Ocean are going in the same direction. Have you given any thought to how your modifications in the ice nucleation are gonna play with PUMA's?
Yeah, I think both Andrew's PUMA's and our modification for the IMP and the SIP signalized that moved the cloud face in the right direction. But we haven't combined both of modification. We could, but Andrew's PUMA right now I don't consider marine organic IMP yet. So, and we are thinking talk about in the chemistry working group that we could also add in the marine organic aerosol into the model, and therefore we can, because that MOA marine organic could be important over that Southern Ocean because there's not a lot of other aerosol type that there. So maybe a marine organic can be important for IMP, and yeah. So we think about to add in the marine organic to the model that we can enable the IMP in fact. But currently the CSM don't have the marine organic also, and also currently for the signal it's include one mechanism at highly emulsive rhyming splinter in the model, but not include other mechanism could be more important at the minus 10 degree also that is not included in the model yet. So that we could yeah combine with our modification with PUMA's, yeah.
Okay, yeah, so Oyvind, I guess, is asking a similar question, and it's one that I would also like to hear your answer to. Is that PUMA's apparently is, as you say, that PUMA's is also including some secondary ice.
That's only one mechanism, like rhyme splintering, like highly emulsive process. Okay. This mechanism is not it's only efficient at -3 to -8 degrees. Outside that, outside that temperature range is not important. So their study found that this other mechanism could be very important, and in the model right now it's a highly emulsive process. Rhyming splinter is not effective, not very effective, and we find out that other mechanisms are more important, which are not represented in the model.
Okay, thanks.
Julio, I'd like to make a comment on this morning's talks, which were mostly about shallow convection, shall we say.
Okay.
There's a very interesting thing coming about. You know, let's take the trade wind cumulus, for example. There's been some trouble with representing them even in numerical weather prediction models. And in fact, I think one thing is missing from these schemes, if you like. Remember in the MCS sort of thing, we are introducing heat and momentum transports by mesoscale circulations, which mesoscale circulations are driven by small scale convection, basically. Well, the same thing happens in the trade winds. There are circulations on scales larger than the clouds themselves, but the type of model is very, very different. In the MCS, it's mostly up shear propagation, but in the trade winds, it's actually the opposite. The clouds tilt downwind. And so that means that the momentum transport is the opposite. So as a matter of fact, I think that the principles we're doing for the deep convection have implications for how we deal with the parameterization of organization in shallow convection, particularly in the tropics. So I'd like you maybe to think about this. I have some ideas on this. And in fact, recently I've had an idea about this, that for observational, verification.
No, thanks. That sounds like an interesting thing to think about.
I think yes, I think it's a very doable thing.
Mm-hmm.
Put this momentum, the mesoscale circulation in the deep convection is one type of approach, but the same type of approach with different dynamical modules can be done, for example, for the trade winds. The trade winds, of course, is totally, they're a shear parallel organization, and the clouds, as I say, tilt the opposite way from the MCS, not backwards. So I think we can do something with this.
Okay.
Hey, Mitch, just a quick follow-up. And all you are imposing for the deep convection MCS parameterization is just heating. But you keep on talking about the importance of convective momentum transport.
No, yes. Can I? No, actually, we put both heat and momentum signal tendencies in there. If you think back to today, Jack showed the momentum transport effects. It's both heat. We can put heating on its own, momentum on its own, and heating plus momentum, and we've done those things. No, we do momentum. Yes.
Okay. Well, I'd be interested in exploring this for some of the MF work I'm working on. So
I think that'd be very, very interesting. And remember, there are different kinds of organization. We're dealing mostly with the shear perpendicular type of structures, but the shear parallel is also very important in the tropics. So I think there's a whole wealth of things that could be done both in modeling, observation, and parameterization, and this whole business. Yeah.
I do have a little side question on whether these heating profiles and momentum profiles that you're adding, have you ever checked whether they're violating CAM's energy conservation? There's a print energy checks, and I'm wondering if it's conserving energy in the column.
Yes, I did. I added like energy check to ensure I don't take anything out or add anything in.
Excellent. Okay.
Yeah.
Thanks, Jack. That was good.
Are there more comments, questions on the talks from either this morning or from the last session? Okay. It seems well. I think if there aren't any, we are close to the end of the session in any case. So I'll talk slowly, but I think at this point maybe we should just adjourn for the day, and we'll start again tomorrow at 9 o'clock. We'll be having a session on chemistry and aerosols from 9 to about 11. Then we'll have a seminar from Isla Simpson on what we can expect for the future of North American hydroclimate. This is part of the CGD seminar series. After that, we'll have some talks on the upper atmosphere, and then another session after that on CSM and CAM physics sensitivities. So I want to go ahead and thank the speakers from today again, and to all the participants. I think we've had some good discussions, and thank you all very much, and we'll see you tomorrow morning. All right, goodbye.